Coca Cola, Gatorade, and Fanta begin as liquids, but are built for completely different moments. One carries a guarded cola formula, one is engineered to replenish athletes, and one turns bold fruit flavor into a burst of taste. In this video, we enter the production lines behind these iconic drinks and uncover how 3 distinct recipes are secretly blended worldwide. Coca Cola begins as a concentrated dark syrup folding into a polished stainless steel blending tank. A measured volume of treated water is already moving inside the vessel. The agitator beneath the surface creates a broad circular current. Sweetener enters through a controlled feed line. When granulated sugar is used, the crystals descend into the moving water and dissolve as the liquid warms. When liquid sweetener is used, it enters as a dense stream and disappears into the rotating base. The syrup grows heavier as the dissolved solids increase. Its surface changes from quick, watery ripples to slower, glossy waves. Temperature probes and load cells monitor the batch while the mixer continues turning. The goal is a smooth, sweet base with no undissolved material remaining. This liquid passes through fine filtration before flavor concentrate is added. Filters capture any remaining particles that could interfere with downstream pumps, valves, flow meters, or filler heads. The clarified syrup enters a finished syrup tank through enclosed pipework. Coca-Cola concentrate is then metered into the sweetened base. It arrives in a precisely controlled stream, carrying the flavor system, caramel color, and formula components that define the beverage. As the concentrate enters, the syrup darkens rapidly. The agitator pulls the darker stream downward and folds it through the full tank volume. The liquid becomes dense, deep brown, and strongly concentrated. It is not yet Coca-Cola at drinking strength. It contains the flavor and sweetness in a reduced liquid volume, designed to be diluted accurately later in the line. The water used for this process has already passed through a separate preparation route. Incoming water moves through screens and particle filters. Activated carbon removes unwanted odor and taste variation. Fine polishing stages stabilize clarity and mineral behavior. The treated water is held in closed tanks until pumps send it either to syrup production or final blending. The finished syrup now leaves its tank and enters a proportioning system. One pipeline carries the concentrated syrup. Another carries treated water. Both streams run through precision flow meters before they are allowed to combine. Automatic valves continually adjust the 2 flows. The proportioner does not blend by rough volume. It holds the formula ratio while pumps speed up, slow down, or respond to changes in line pressure. The dark syrup meets the clear water inside a closed mixing chamber and instantly thins into a finished strength beverage base. At this point, the liquid has the proper color, sweetness, acidity, and flavor concentration, but it is still flat. It moves through stainless steel pipes toward temperature control equipment. The beverage enters a plate heat exchanger. Thin metal plates separate the flowing drink from a cold circulating medium. Heat transfers quickly through the steel. The Coca-Cola stream emerges chilled while remaining fully enclosed. Cold liquid is essential for the next stage. Carbon dioxide dissolves more efficiently at low temperature, and the chilled beverage produces less foam when it reaches the filler. A warm carbonated drink would release gas too aggressively during packaging. Before carbon dioxide is introduced, excess dissolved air may be reduced. The beverage, or the water stream, passes through a deaeration vessel operating under reduced pressure. Tiny bubbles leave the liquid and collect above it. The stream exits with less unwanted gas and more capacity for controlled carbonation. Carbon dioxide arrives through pressure-regulated lines. The gas is prepared and delivered into the carbonator, where chilled Coca-Cola flows under controlled pressure. Carbon dioxide dissolves into the dark liquid, creating the sharp, sparkling texture of the finished drink. From the carbonator onward, the beverage stays sealed inside pressurized pipework. Any uncontrolled release of pressure would allow carbonation to escape as foam. The liquid flows directly toward the filler bowl, while containers are prepared on adjacent lines. For a can format, empty aluminum cans arrive already shaped and printed. They move quickly between guide rails and enter an inversion rinser. Curved tracks turn each can upside down. Filtered air or rinsing fluid clears the inside. The cans drain, rotate upright again, and continue toward the filler in tightly spaced rows. For a plastic bottle format, the container begins as a PET preform. The preform resembles a small, thick tube with a finished threaded neck. Feeders orient the preforms and place them onto carriers that move through an infrared heating oven. The preforms rotate beneath heating lamps. Their bodies soften evenly, while the neck area stays dimensionally stable. Once heated, each preform transfers into a chilled steel mold containing the exact shape of the finished bottle. A stretch rod pushes through the softened preform and pulls it downward. Compressed air then bursts into the interior. The plastic expands outward until it contacts the mold wall. Shoulders, label panels, base petals, and pressure supporting curves appear in less than a second. The mold opens and the newly formed bottle exits held beneath its neck ring. Lightweight bottles move through air conveyors, pushed forward by controlled air streams rather than standing heavily on their bases. This keeps them aligned before they contain liquid. The bottles enter a rinsing station. Grippers lift them by their necks and invert them. Filtered air or treated rinse water is directed into each interior. After a brief draining motion, the bottles turn upright and move toward the filler. Glass bottle lines follow another route. Formed bottles pass under inspection lights and camera systems before filling. Their mouths, bases, sidewalls, and interiors are examined. Any bottle with a crack, chip, deformation, or internal contamination is removed from the flow. The filler is a rotating carousel with many filling valves arranged around its circumference. Pressurized carbonated Coca Cola enters the filler bowl above the containers. Star wheels separate incoming bottles or cans into equal intervals and guide each package beneath a valve. For a bottle, the opening presses into sealing contact with the filling valve. The pressure inside the empty container is equalized with the filler environment before beverage flow begins. This prevents an immediate burst of foam when the carbonated liquid enters. The valve opens and Coca-Cola flows into the container in a calm, controlled stream. The liquid is directed to reduce splashing and turbulence. In a clear bottle, the dark beverage climbs upward while small bubbles cling briefly to the interior wall. When the target fill level is reached, the valve closes. A precisely controlled headspace remains above the liquid. The container leaves the filler and moves immediately toward closure equipment while the drink is still cold and pressurized. Plastic bottles receive screw caps. Caps are supplied in bulk to a sorter that arranges them in one direction. A chute delivers them to rotating capping heads. Each head places a cap over the bottle neck and turns it to a controlled torque. The tamper band slides past the neck ring and locks beneath it. Glass bottles receive crown caps. A metal crown is positioned on the bottle mouth and forced downward by a capping head. Its ridged skirt folds tightly beneath the glass finish, forming a gas-tight closure. Filled cans receive aluminum lids at the seaming machine. A lid is placed on every open can. Rotating seaming rolls fold the lid edge and can flange together. The first operation hooks the metal layers. The second compresses them into a narrow double seam that seals carbonation inside. The sealed containers pass directly through inspection. Sensors examine fill height. Cameras verify cap presence, cap angle, crown placement, lid position, printed surfaces, and container shape. Conseam monitoring equipment checks the closure profile. A container outside the set limits is removed without stopping the conveyor. Electrolyte salts fall into a rushing stream of treated water, dissolving before the liquid reaches the main Gatorade blending tank. The crystals are small, pale, and precisely measured. They enter through a controlled powder feeder, not in loose scoops. As the water moves through the inline mixer, turbulence pulls the particles apart and distributes them through the stream. The liquid remains clear, while its dissolved mineral content changes. Gatorade is built as a non-carbonated sports drink. Unlike Coca Cola or Pepsi, it does not need a pressurized carbonator or foam-controlled filling valves. Its production line concentrates on dissolving sugars and electrolytes, creating bright flavor and color, controlling acidity, heat-treating the beverage, filling it into bottles, sealing it, cooling it, labeling it, and packing it. The water has already passed through treatment equipment before it reaches ingredient blending. Incoming water moves through particle filters that remove suspended material. Activated carbon beds reduce unwanted taste and odor. Polishing filters and conditioning stages bring the water to a consistent clarity and mineral profile. The treated water flows into enclosed stainless steel storage tanks. Level sensors monitor volume. Temperature probes track the liquid condition. Pumps draw from these tanks in measured streams, supplying both the ingredient preparation area and the final blending system. Sugar or another specified sweetener is prepared in a separate dissolving tank. Treated water enters first. A large agitator begins turning, creating a broad, rotating flow. Sweetener is delivered into this movement through bulk dosing equipment. When granulated sugar is used, the crystals strike the water surface and vanish into the circulating liquid. Mild heat helps dissolve them quickly. The liquid becomes heavier and glossier as the sugar concentration increases. It moves against the tank wall in slower waves than plain water. The sweetened solution passes through filtration. Fine screens or cartridge filters remove any material that has not dissolved completely. The clear syrup then moves toward the main blend tank through sanitary pipework. The electrolyte solution joins the syrup stream under controlled conditions. Sodium and potassium containing ingredients are dissolved so they do not remain as grit or settle inside the tank. Their addition is small compared with the full beverage volume, so meters and dosing pumps control each stream closely. Acid ingredients are added next. They supply the bright sharpness that balances sweetness and supports the fruit-flavored profile. A metered acid solution enters below the liquid surface, and the agitator immediately folds it into the moving beverage base. Flavor concentrate follows through a closed line. Lemon lime, orange, fruit punch, blue raspberry style, or other variants are produced by changing the programmed flavor and color additions, while the basic liquid handling equipment remains similar. The concentrate enters in a narrow stream and disperses rapidly. Color is measured with the same precision. A small quantity can transform a large tank of nearly clear beverage into vivid orange, red, yellow-green, or blue liquid. The agitator keeps the color moving until the shade is consistent throughout the vessel. The blended drink is now close to finished Gatorade in flavor, sweetness, electrolyte concentration, acidity, and appearance. Samples may be drawn automatically through inline measurement systems that monitor flow, density, temperature, and blending consistency before the liquid proceeds. Because the drink is non-carbonated, its preparation differs sharply from sparkling soft drinks. There is no carbon dioxide injection stage and no requirement to keep gas dissolved under filler pressure. Instead, a shelf-stable bottling line commonly relies on controlled heat treatment and hot filling. The liquid is pumped toward a heat exchanger. Inside, the beverage passes through thin metal channels while a heating medium flows through adjacent channels. Heat transfers rapidly into the drink without exposing it to the surrounding room. The temperature rises to the programmed filling range. The beverage stays fluid and clear, but it is now hot enough for the hot fill packaging sequence. Pumps maintain steady movement through the closed system, so the heated drink reaches the filler without unnecessary cooling. While the beverage is being blended and heated, bottles are being formed nearby. Plastic bottles begin as PET preforms. Each preform resembles a short, thick tube with a fully molded threaded neck. The cap sealing surface, threads, and support ring already exist. Only the bottle body still needs to be expanded. Preforms tumble into an orienting feeder. Mechanical tracks align them and deliver them one by one into a heating oven. Infrared lamps warm the thick plastic body as carriers rotate each. Preform. Rotation prevents hot spots and keeps wall thickness balanced during stretching. The heated preform enters a blow molding station. A metal mold closes around it, carrying the exact outline of the final Gatorade bottle, including its shoulder profile, label area, grip details, and stable base. A stretch rod extends down through the softened preform. It pulls the plastic lengthwise. High-pressure air then expands the plastic outward until it presses firmly against the mold interior. The compact preform becomes a full-size bottle in less than a second. The mold opens. The finished bottle leaves by its neck ring and transfers into air conveyors. Streams of air push the lightweight containers forward while guide rails hold their necks in alignment. The empty bottles travel toward rinsing and filling without needing to stand heavily on their bases. At the bottle rinser, each container is gripped, inverted, and cleaned internally with filtered air or treated rinsing fluid. It turns upright again and enters the filler in a clean, open condition. the hot Gatorade stream arrives at the filling machine through insulated piping. Because the beverage is not carbonated, the filler does not need to balance gas pressure inside each empty bottle. The main requirement is accurate volume, controlled temperature, and smooth handling of the hot liquid. A star wheel spaces the bottles evenly around a rotary filling carousel. Each bottle aligns beneath a filling nozzle. The nozzle opens, and the brightly colored beverage flows downward into the container. The bottle fills rapidly from the base upward. Orange, red, blue, or yellow-green liquid climbs through the clear plastic wall. Sensors or calibrated filling controls stop the flow when the required volume is reached, leaving the correct headspace below the cap. The filled bottle moves immediately to capping. Plastic caps arrive through a sorting bowl that turns every closure into the same orientation. A chute carries them toward rotating capping heads. Each head picks up one cap, lowers it over the bottleneck, and turns it to a controlled torque. The cap liner presses against the sealing surface. The tamper band slips over the neck ring and locks beneath it. The hot beverage is now enclosed. On a hot fill line, the newly capped bottles may be inverted or tilted through a controlled section of conveyor. This brings hot liquid into brief contact with the inner cap and upper neck surfaces. The bottles then return upright and travel toward cooling. The hot bottles cannot proceed directly to labeling or packing. Their liquid temperature must fall, and the plastic container must settle into its final stable shape. The bottles enter a cooling tunnel where water sprays descend in stages. The first cooling zones use warmer water to avoid a sudden thermal shock. Later zones apply progressively cooler water. Heat leaves the drink and bottle wall gradually. The bottles move continuously as spray nozzles shower the caps, shoulders, sides, and bases. As cooling continues, the beverage approaches normal handling temperature. The PET walls become firm and stable. Any slight vacuum response created by cooling is accommodated by the bottle design, which may include shaped panels or structural contours. The cooled bottles exit wet. Air knives immediately direct thin, powerful sheets of air across the container surfaces. Water strips away from the cap edge, shoulders, label area, and base. Dry bottles are essential because labels and packaging film must grip cleanly. Inspection equipment checks the filled and capped product. Cameras examine cap presence, cap alignment, tamper band position, bottle shape, and liquid appearance. Fill level sensors verify that each bottle contains the correct quantity. Any rejected bottle is diverted from the moving line. The dry bottles now reach labeling. In one common system, printed shrink sleeves are opened and lowered over each bottle. The loose sleeve surrounds the container before it enters a steam or heat tunnel. Inside the tunnel, heat causes the sleeve film to contract. It draws tightly around the bottle profile, following curves, shoulders, and grip contours. The printed design becomes smooth and aligned against the plastic surface. Other bottle formats use wraparound, roll-fed labels. Printed film unwinds, is cut into individual labels, receives adhesive at controlled contact points, and wraps around the rotating bottle body. Rollers smooth the label before the bottle continues. A coding machine adds production information. An inkjet printer fires tiny droplets onto the cap, shoulder, label, or bottle surface as the container moves past. Vision equipment can verify code presence without stopping the conveyor. Bottles then divide into parallel lanes for secondary packaging. Guide rails direct the flow, while timing screws establish equal spacing. Collators gather the containers into exact groups for tray packs, shrink bundles, or cartons. For shrink-wrapped packs, film feeds around the collected bottles. The group enters a heat tunnel. Warm air tightens the film around the bottle shoulders and bases, turning separate containers into a stable bundle. For tray packs, a corrugated blank slides beneath the bottles. Folding guides raise the tray edges around the base of the group. Film may then wrap the full assembly, creating support beneath and tension around the outside. Finished packs travel toward palletizing. Turning conveyors rotate selected bundles, so each layer forms a stable pattern. A layer table gathers the packs, presses them into alignment, and transfers the complete layer onto a pallet. A clear PET preform rotates beneath infrared lamps until its thick plastic body becomes soft enough to stretch. It is still only a compact tube with a finished threaded neck. The lower portion contains the material needed for an entire Fanta bottle. As the preform advances through the oven, its neck remains firm while the body heats evenly on every side. A transfer wheel lifts the warm preform into a steel mold. The mold closes around it. A stretch rod drives downward through the center, pulling the plastic lengthwise. Compressed air enters immediately afterward, expanding the softened material against the chilled mold wall. In less than a second, the short preform becomes a full bottle. Its base forms into pressure-resistant feet. Its shoulders curve into place. Its label panel and grip contours appear as the plastic cools against the mold surface. The mold opens. The empty bottle leaves suspended beneath its neck ring. Air conveyors push it forward in a light, fast-moving stream, keeping each bottle upright without crushing its thin body. While bottles are being formed, the orange drink is being assembled inside stainless steel equipment. The first liquid entering the beverage line is treated water. Incoming water passes through particle filtration, activated carbon treatment, and fine polishing stages. Suspended material disappears. Unwanted odor and taste variation are removed. The finished water flows into sealed storage tanks fitted with level and temperature sensors. One measured portion of treated water is pumped into a syrup dissolving tank. The agitator starts turning before sweetener enters. Its blades draw the liquid downward, forcing it outward along the rounded tank wall and back upward in a smooth circulation pattern. Granulated sugar, liquid sugar, or another specified sweetener is metered into the moving water. When crystals are used, they sink into the rotating liquid and dissolve as controlled heat assists the process. The mixture grows denser. The surface becomes glossy, rolling in slow folds rather than quick splashes. The sweet base passes through fine filtration. Any undissolved particles are removed before they can interfere with pumps, meters, or filling valves. The filtered syrup then reaches the flavor-building vessel. Fanta orange flavor concentrate enters through a closed dosing line. The quantity is small compared with the syrup volume, so metering accuracy is essential. The concentrate disperses below the surface, while the agitator continues circulating the liquid. Color components join the syrup in measured additions. The previously pale mixture becomes a strong, brilliant orange. At this stage, the color is deeper than the finished beverage because the syrup has not yet been diluted to its final strength. Acid ingredients are dissolved and introduced into the moving blend. They create the sharp citrus character that balances the sweet base. The liquid is mixed until its acidity, flavor, and color are evenly distributed throughout the tank. Orange-flavored carbonated drinks can also contain an emulsified flavor system. Citrus oils do not remain evenly dispersed in water without preparation. They are broken into extremely small droplets and held in suspension by the formula structure. This can give the liquid a fuller, softly cloudy orange appearance. The emulsion must be handled gently. Powerful enough mixing spreads it evenly, but excessive mechanical force can disturb the droplet system. The agitator, therefore, runs at a controlled speed, folding the syrup repeatedly without tearing apart the intended texture. The completed syrup is now intensely sweet, acidic, aromatic, and orange. It is still too concentrated for filling. A sanitary pump sends it toward the proportioning unit, while a second pipeline brings treated water from storage. Flow meters read both streams continuously. The proportioner adjusts valves in tiny automatic movements, maintaining the required syrup-to-water ratio as production continues. Neither stream is allowed to drift independently. Inside the mixing chamber, concentrated orange syrup meets clear treated water. The color brightens instantly. The viscosity drops. The liquid becomes finished strength Fanta, carrying its final sweetness, fruit flavor, acidity, and appearance, but it remains flat. The beverage enters a chilling system. It travels through narrow passages in a plate heat exchanger. Cold circulating fluid moves through adjacent passages, separated from the drink by thin stainless steel plates. Heat leaves the beverage quickly while it remains enclosed. The lowered temperature prepares the drink for carbonation. Cold liquid absorbs carbon dioxide efficiently and behaves more calmly in the filling machine. Without sufficient chilling, The drink would release gas too quickly and produce excessive foam during packaging. The liquid may move through a deaeration stage before carbonation. Reduced pressure draws dissolved air out of the beverage. Tiny gas bubbles emerge from the stream, rise through the chamber, and separate from the liquid. Carbon dioxide arrives through regulated gas lines. Inside the carbonator, the chilled orange drink flows under pressure while the gas dissolves into it. The liquid becomes sparkling, with carbon dioxide held inside rather than escaping as visible bubbles. From this point onward, the finished Fanta remains in closed pressurized pipework. It flows directly toward the filler, while the empty bottles approach from the forming line. Before entering the filler, each PET bottle is cleaned internally. Neck grippers lift and invert the containers. Filtered air or treated rinsing fluid enters through nozzles, clearing the inside surface. The bottles drain briefly, rotate upright, and transfer forward. The rotary filler receives bottles through a star wheel. Each bottle is separated into an exact position and guided beneath a filling valve. The bottle rises into contact with the valve as the carousel continues rotating. Pressure is balanced before liquid enters. This keeps the carbonated beverage from rushing into the empty bottle in a burst of foam. Once the internal conditions are stable, the valve opens. Orange Fanta flows smoothly down the bottle wall. The bright liquid climbs upward through the transparent plastic while fine bubbles remain suspended inside it. At the target fill height, the valve closes, leaving the required space beneath the cap. The filled bottle travels immediately into capping. Plastic closures arrive in bulk and enter a sorting system. The sorter turns every cap into the correct orientation and delivers them down a chute toward rotating capping heads. A head collects one cap, places it onto the bottleneck, and tightens it with controlled torque. The sealing surface compresses beneath the cap. The tamper band slips over the neck ring and locks underneath it. Carbonated Fanta is now enclosed inside the bottle. Other Fanta formats follow parallel package routes. Aluminum cans arrive open at the top, pass through air rinsing, and receive the chilled beverage at a can filler. A lid is positioned over each filled can, then seaming rolls. Fold the lid curl and can flange into a pressure-tight double seam. Glass bottles arrive already formed. Cameras examine their mouths, walls, bases, and interiors before rinsing and filling. After receiving carbonated Fanta, they pass beneath a crown capper that presses and crimps a metal closure over each bottle mouth. Every sealed package enters inspection. Sensors verify fill height. Cameras check cap position, tamper bands, can seams, crown caps, bottle shape, and container condition. A rejected unit is diverted from the conveyor while correctly sealed packages continue at full line. Snickers is built as a layered bar where each layer is made in a separate process stream and then assembled in a continuous line before chocolate enrobing and final packaging. The process begins with ingredient staging because each component behaves differently under heat and shear. Sugar and glucose syrup are held in heated tanks so they pump at stable viscosity. Cocoa butter and chocolate liquor are tempered in separate vessels to control crystal form. Milk powders and cocoa powders are sieved to remove lumps that would create specks. Roasted peanuts are cleaned and graded so the size band stays consistent for even topping. Nougat production starts with preparing a cooked syrup that will later be whipped into a light structure. Sugar syrup and glucose syrup are metered into a cooker and heated to a target solids level. Temperature control is tight because syrup concentration sets final chew. The hot syrup is discharged into a mixing zone where it meets a protein foam stream. The foam is typically built from egg albumin or similar proteins that can trap air under shear. Foam generation uses a high-speed whip that pulls in air and creates small, stable bubbles. The protein solution is mixed to a defined concentration and then aerated until density hits a set point. This foam is fed continuously so the nougat texture stays steady. When hot syrup meets the foam, it partially cooks the proteins and locks bubble walls. This creates a stable aerated matrix that will set as it cools. Fat is added during nougat mixing to soften bite and reduce stickiness. The fat is melted and injected as a thin stream so it disperses without breaking the foam. Flavor additions are injected at this stage because heat is lower than in the cooker. Emulsifiers may be added to stabilize the air-fat water system. The mixer uses folding elements that build uniformity without collapsing the aeration. The finished nougat is still warm and plastic. It is discharged onto a moving belt through a depositing head. The depositor spreads the nougat into a continuous slab with a controlled thickness. Leveling bars and rollers set the slab height. A cooling tunnel then lowers temperature so the nougat gains strength for the next layer. Caramel production runs in parallel because caramel requires its own cook profile. Sugar and glucose syrup are cooked with milk components to build flavor and elasticity. The cook drives Maillard reactions that deepen color and create caramel notes. Solids level is driven high enough that caramel will hold shape. Fat is added to create a smooth texture and to reduce stickiness on cutting surfaces. Caramel is cooled to a depositable temperature that remains fluid but not runny. It is held in a jacketed tank where gentle agitation prevents skin formation. From there, it feeds a depositing head positioned above the nougat slab. The head lays down a continuous ribbon and spreads it into an even sheet. Thickness is controlled because caramel sets the bar chew and the layer must remain uniform across the belt. Peanut preparation is treated as a critical control point because nut texture drives the bite and also affects line flow. Peanuts are roasted to a target color and moisture. After roasting, they are cooled, so residual heat does not melt chocolate later. They pass through screens that remove fines and broken bits. Oversized clusters are removed to prevent peaks that can pierce the chocolate coat. Before peanuts are applied, the caramel surface is conditioned so it can hold nuts without sinking. Temperature is managed so caramel is tacky at the surface but stable underneath. Peanuts are metered through a spreader that distributes them across the width of the slab. A light compression step can press nuts into caramel for better adhesion. Compression is kept gentle so nuts do not fracture into sharp fragments. At this stage, the bar has its internal structure and it must be shaped into individual pieces. The layered slab passes through a cooling section where the caramel firms further. The goal is a slab that cuts cleanly without smearing. Cooling is staged so the outside does not become brittle while the core remains soft. Belt speed and tunnel temperature are coordinated to hit the target firmness at the cutter. Cutting begins with edge trimming because slab edges often have thickness variation. Rotary knives remove edges and return them to rework streams. The main slab then enters a guillotine or rotary cutter that slices it into long ropes. A second cutter slices the ropes into bar lengths, knife temperature, and coating are managed so caramel does not stick. Cut accuracy is monitored because bar weight must remain consistent for packaging. Bars are then transferred onto an enrobing line. Transfer is designed to avoid deformation because the bars are still relatively soft. A flighted belt or gentle diverter aligns bars with spacing that matches the enrober curtain. Spacing matters because chocolate flow must wrap each bar without bridges. Bars may pass through a brief chill to firm surfaces before chocolate contact. Chocolate preparation is a separate discipline because the coating must snap and shine. Chocolate is melted and then tempered to form stable crystals. Tempering creates a seed crystal population that guides solidification. Temperature is adjusted in small steps through heat exchangers. Viscosity is checked because it controls curtain thickness and coverage. Enrobing applies chocolate in a continuous curtain that coats the top and sides. Bars ride through the curtain and the underside is coated by a bottoming system. A wire mesh belt allows excess chocolate to fall away. Air knives or blowers remove extra chocolate and smooth the surface. This step also shapes the foot that forms under the bar. Air pressure and nozzle angle control how sharp the edges look. If the product design includes a patterned top, the line uses a stringer. A stringer drizzles thin lines of chocolate across the surface. Line spacing and flow are controlled to keep the pattern consistent. The drizzle must bond to the base coat before it sets. Timing is therefore synchronized with cooling. After enrobing the bars, enter a cooling tunnel that solidifies the chocolate coat. Cooling is staged to prevent bloom and cracks. The first zone sets the surface quickly so the coating does not slump. The next zones pull heat out gradually so crystals grow in the desired form. Airflow is controlled to avoid condensation. The bars exit at a temperature that keeps the chocolate hard enough for wrapping. During cooling, the internal layers also continue to equilibrate. Nougat firms as its foam matrix stabilizes. Caramel sets into an elastic sheet that resists flow. Moisture migration between layers is managed by formulation and by process temperatures. The chocolate coat acts as a moisture barrier once fully set. A stable barrier helps maintain texture through storage. Quality checks are integrated as the line runs. Vision systems check bar shape and coating coverage. Weight checks confirm portion control from the cutters. Metal detection protects the final product flow. Bars with coating voids or broken corners are diverted. Rework handling is designed so chocolate can be remelted and core materials can be redirected appropriately. Wrapping begins once bars are fully set. Bars are indexed into a flow wrapper that forms film around each bar. The wrapper folds the film and creates end seals. Seal jaws apply heat for a defined dwell time. Film tension is controlled so the wrap sits tight without crushing the bar. Registration marks on the film guide print alignment with the bar. After primary wrapping bars may be packed into multi-packs. Collation systems group a defined count and then overwrap or carton them. Grouping uses timing screws and gating to maintain spacing. Overwrap uses a second film and a second sealing cycle. Cartoning erects cartons and loads bars with pushers. Each step is tuned to avoid scuffing the chocolate surface. Finished packs go to case packing. Cases are loaded in patterns that protect seals and prevent crushing. Cases are sealed and coated for traceability. Palletizing stacks cases to reduce movement during transport. Storage conditions are controlled to keep chocolate stable and to protect texture. Twix is manufactured by building a baked biscuit base, covering it with a controlled caramel layer, then enrobing the assembled sticks in tempered chocolate before wrapping. Biscuit production starts with preparing a dough that will bake into a crisp, low-moisture substrate. Flour is sieved to remove lumps and to aerate it for consistent hydration. Sugar is screened so crystal size stays uniform and does not tear gluten strands during mixing. Fats are brought to a controlled plastic consistency so they cream smoothly rather than smearing. Leavening salts are weighed precisely because they set lift and porosity. Mixing begins with creaming fat and sugar to create a uniform fat phase that holds small air cells. The mixer uses a paddle action that shears and folds. Air incorporation is controlled because too much air weakens the biscuit and makes it fragile during later handling. Too little air yields a dense biscuit that can be hard and overly brittle. Once creaming reaches a stable texture, liquid ingredients are added in a controlled stream so the emulsion stays stable. Dry ingredients are then introduced gradually. Flour and leavening blend into the creamed base and form a dough. Mixing intensity is reduced as flour enters because gluten development must be limited. Excess gluten makes the biscuit tough and causes shrinkage during baking. The end point is a cohesive dough that holds together yet remains short and tender due to the fat content. Dough temperature is controlled because it determines how cleanly the dough sheets. If the dough is warm, the fat softens and the sheet sticks to rollers. If the dough is too cold, it cracks and creates edge defects. The dough is rested briefly, so moisture equalizes and the dough relaxes. Relaxation improves sheet uniformity and reduces snapback. Sheeting converts the dough into a continuous band at a target thickness. The dough passes through a series of reduction rollers that gradually thin it. Each roller gap is set to avoid tearing. The sheet then passes through gauge rollers that lock thickness. Thickness control is critical because it sets biscuit mass and later caramel ratio. Surface flour dusting is used sparingly to prevent sticking without drying the surface. The sheet enters a cutting and docking station. Cutters slice the sheet into long, narrow biscuit sticks. Docking pins punch small holes through the surface. Docking vents steam during baking and prevents blistering. Hole pattern also controls the biscuit's final flatness, which matters for caramel deposition. Cut sticks transfer onto an oven band and enter a multi-zone tunnel oven. Baking begins with rapid heat input that melts fats and sets the dough shape. As temperature rises, water evaporates and structure forms. Leavening gases expand and create small pores. The oven zones are tuned so the biscuit dries to low moisture without scorching edges. Color development is controlled by time and temperature and sugar content. The goal is a light golden biscuit that stays neutral under chocolate. Overbaking darkens the biscuit and can add bitter notes. Underbaking leaves moisture that later softens the bar. Moisture control is therefore a key specification. The biscuit exits the oven and moves into a cooling tunnel. Cooling is staged, so the biscuit does not crack from thermal shock. Airflow removes heat gradually. The biscuit becomes crisp as moisture drops and fats resolidify. After cooling, the sticks are firm enough for coating, and they also become a stable platform that will not deform under caramel load. Biscuit handling includes alignment and spacing. Sticks are conveyed in lanes, and spacing is controlled by timing belts. Broken sticks are screened out because they cannot be coated uniformly. Thickness and length checks confirm the cutter and oven remain stable. The goal is a consistent feed into the caramel section. Caramel production runs in parallel. Sugar and glucose syrup are cooked with milk components to create a chewy caramel with a defined solids level. Cooking develops color and flavor through controlled Maillard reactions. Solids must be high enough that caramel holds shape. Solids must not be so high that caramel becomes glassy and cracks. Fat is added to smooth texture and reduce stickiness. Caramel is cooled from cooking temperature to a depositor temperature that remains fluid. A jacketed holding tank maintains temperature with gentle agitation. The agitation prevents skin formation and keeps the caramel uniform. Viscosity control is crucial because deposition must create a flat, even layer. If caramel is too thin, it runs off edges. If it is too thick, it forms ridges and traps air. Caramel deposition applies a continuous sheet or a ribbon onto the biscuit sticks. A depositor head sits above the moving lanes. It extrudes caramel through a slot die or through multiple nozzles that merge into a sheet. The caramel lands on the biscuit and spreads. A leveling bar can smooth the top and set thickness. Thickness is controlled because it defines bite and overall bar weight. Adhesion between caramel and biscuit depends on surface condition. If the biscuit surface is too dusty, caramel can delaminate. If the biscuit is too warm, caramel can sink and create uneven thickness. The line controls biscuit temperature before deposition so the surface is firm and receptive. Caramel temperature is also tuned so it bonds without soaking. After deposition, the caramel must be set enough for chocolate coating. Setting is done through a cooling tunnel. Cooling reduces caramel flow and increases elasticity. Cooling also prevents caramel from sticking to enrobing equipment. The cooling profile is staged, so the caramel surface firms first, while the interior stays slightly compliant. This prevents surface cracking. Once the caramel-topped biscuit reaches the enrobing section, the product is treated as a composite stick. It must stay aligned, so chocolate coverage is uniform. Spacing is adjusted to match the chocolate curtain. The underside is still biscuit, so bottom coating must seal it to prevent moisture pickup. Chocolate preparation is built around tempering. Chocolate is melted and then cooled under controlled agitation to form stable seed crystals. It is then reheated slightly to a working temperature. This produces a chocolate that sets with gloss and snap. Viscosity is adjusted by cocoa butter level and by temperature. Stable viscosity keeps curtain thickness consistent. Enrobing applies chocolate as a flowing curtain that covers the top and sides. The sticks pass through the curtain on a wire belt. Bottoming rollers or a chocolate bath coats the underside. Excess chocolate drains through the belt. Air knives remove extra chocolate and define edges. Air knife settings also influence how much chocolate remains on corners. Corner thickness matters for bite and for setting time. After enrobing, the surface can be decorated or left smooth depending on format. If a pattern is desired, a stringer drizzles fine lines across the surface. The drizzle must be applied while the base coat is still tacky enough to bond. Flow rate and nozzle spacing control stripe. Definition. The product then moves immediately into the cooling tunnel. Cooling sets the chocolate coat and locks the bar structure. The first cooling zone sets the surface quickly so chocolate does not slump. Subsequent zones cool more gradually so crystals form in the desired stable state. Cooling air temperature and humidity are controlled so condensation does not form. The bars exit with a hard shell that protects the interior. During cooling, the biscuit remains crisp and the caramel equilibrates. Moisture migration is minimized because biscuit is low moisture and caramel is higher moisture. The chocolate coat acts as a barrier and slows migration. Caramel formulation also limits free water so the biscuit stays crisp over time. The layer interfaces are therefore both formulation and process dependent. Smarties are manufactured by building a hard sugar shell around a shaped chocolate center, then applying precise color layers, then polishing to a stable gloss before packaging. The process begins with chocolate preparation because the center controls final shape and shell growth. Cocoa solids, cocoa butter, sugar, and milk ingredients are combined in a mixing stage to create a uniform chocolate mass. Refining follows to reduce particle size, so the chocolate feels smooth rather than sandy. The refined mass is then conked, where heat and shear drive off moisture and unwanted volatiles while distributing fat evenly. After conching, the chocolate is tempered to form stable cocoa butter crystals. Tempering is essential because the centers must hold shape during shell building and must release cleanly from molds or forming belts. Center forming can be done by molding or by depositing. In a molded approach, tempered chocolate is dosed into molds shaped as small, flattened discs. The molds are vibrated so air bubbles rise and the surface levels. Cooling then solidifies the centers until they are strong enough to demold. In a deposited approach, tempered chocolate is extruded or deposited onto a cooled belt in small portions. The portions are shaped by rollers or by controlled vibration to achieve the signature lens shape. The key is uniform mass because shell thickness depends on surface area and tumbling behavior. Once the centers are formed, they are conditioned before panning. Conditioning brings temperature to a narrow band where the chocolate stays solid and does not sweat. If the centers are too warm, they can soften and smear during tumbling. If they are too cold, they can fracture at edges. Conditioning is done with controlled air that stabilizes temperature without adding humidity. Shell building starts in rotating pans or perforated coating drums. The chocolate centers enter as a moving bed that continuously rolls. This rolling action is the foundation of uniform shells because every surface must see the same coating cycles. The shell is grown through many small additions rather than one thick coat. Each addition is followed by drying, so the layer sets before the next one lands. The earliest layers are a sealing stage. A thin syrup is applied to create adhesion between the chocolate surface and the sugar structure. The syrup is sprayed as a fine mist, so it spreads quickly. Dry air then removes water and begins crystallization at the surface. The drum speed is tuned so pieces separate while wet and do not form twins. After sealing, the process shifts to bulk shell growth. A heavier sugar syrup is sprayed and then fine sugar powder is often dusted. The powder absorbs moisture and increases build rate. Airflow continues to dry and promote crystallization. This cycle repeats many times. The shell thickens gradually and the sound of tumbling becomes sharper as surfaces harden. Crystallization control is central to shell quality. If layers crystallize too fast, the surface can trap moisture and later pit. If layers crystallize too slowly, the surface stays tacky and pieces can stick. Air temperature, airflow rate, and humidity are set to keep crystallization steady. Syrup concentration is also controlled because higher solids set faster but can create roughness. Lower solids spread better but demand longer drying. As the shell approaches target thickness, the process emphasizes smoothness. Spray volumes per cycle are reduced and drying time is increased. This refines surface texture and reduces micro ridges. At this stage, the centers also must remain stable. Excess heat in the pan can soften chocolate and cause flat spots. The line therefore balances drying air temperature against chocolate melt risk. Color is built as part of the outer shell rather than in the chocolate. Color solutions are prepared in tanks with controlled concentration. They are filtered to remove undissolved particles that could create specks. Color is applied in thin layers, like the shell itself. A colored syrup or a color solution is sprayed and then dried. Multiple passes deepen saturation while keeping the surface even. Color application is scheduled carefully. Applying color too early can bury it under later clear layers and mute shade. Applying color too late can create blotches because the shell surface is already very hard and less receptive. Many processes use a staged approach where color is introduced after the shell has enough thickness to protect the chocolate. Then color is reinforced through several light cycles. Because Smarties are produced in multiple colors, the line often runs colors separately. Each color run uses its own color solution and its own endpoint checks. The drum and spray circuits are cleaned between colors to prevent cross-tint. Color control relies on concentration and on the number of passes and on drying conditions. Optical measurements compare shade against targets, and adjustments are made by changing spray rate or pass count. Once color is complete, the shell is finished with protective layers. A clear syrup layer can be applied to smooth the surface and lock pigment. This is followed by additional drying to set hardness. Hardness matters because it determines crunch and resistance to scuffing in packaging. The final shell must be hard, yet not so brittle that it chips under impact. After the shell build, the pieces are conditioned for polishing. Conditioning equalizes moisture across the shell thickness. This reduces internal stress that can cause fine cracks. It also stabilizes surface tack, so polishing films spread evenly. Conditioning is done in bins or tunnels with controlled air. The goal is a stable moisture state rather than maximum dryness. Polishing creates the familiar gloss. Polishing agents are applied in very small amounts in a polishing pan. The pieces tumble gently while a fine mist of polishing solution is introduced. The film spreads across the surface through repeated contact. The polishing layer fills micro pores and reduces friction. This improves shine and improves flow through packaging equipment. Polishing must be balanced with print-free handling. Too little polish leaves a matte surface that scuffs and sheds sugar dust. Too much polish can cause slippery handling issues and can change mouthfeel. The process, therefore, uses short polishing cycles with measured additions. Between additions, the pieces tumble to distribute the film evenly. Some formats include a final dust removal step. Light aspiration pulls away loose sugar dust created during shell growth and screening. Dust removal improves pack cleanliness and reduces haze inside clear packs. It also reduces seal contamination in packaging machines. Sorting and screening follow to remove defects. Vibratory screens remove fines and broken shells. Size sorting ensures each piece stays within a target diameter band. Optical sorting can remove off-color pieces and twins and pieces with chips. The objective is uniform appearance and uniform flow. The finished candies move to packaging through gentle conveying. Candy-coated pieces can chip if drop heights are high. Conveyors use shallow chutes and soft transitions. Hoppers are designed with smooth walls to prevent bridging. Feeding systems aim for steady flow into weighers. Portioning is typically done with multi-head weighers. The weigher distributes candies into many small hoppers. Software selects a combination that hits target weight with minimal deviation. The portion then drops into a bag or tube or box, depending on format. Drop path is designed to reduce impacts that could crack shells. For bag formats, film is formed into a tube and sealed. The portion drops into the tube and then transverse seals create the package. Seal timing keeps candies away from sealed jaws. Seal temperature is tuned for the film so it closes without wrinkles. If the pack is a paperboard carton, the candies drop into the carton through a funnel and the carton is closed by tuck or glue. After primary packaging, the units are coded and inspected. Check weighers confirm weight. Vision systems can confirm seal presence and print placement. Rejected packs are removed automatically so the line keeps running. Finished packs are then case packed and palletized. Ferrero Rocher is manufactured by assembling a layered sphere where a crisp wafer shell surrounds a hazelnut scented in hazelnut cocoa cream. Then the sphere is coated in chocolate and finished with chopped hazelnuts before controlled cooling and wrapping. Hazelnut preparation starts the process because nut size and roast level determine the core crunch and the geometry of the finished piece. Raw hazelnuts are cleaned using screens that remove stones and broken shell fragments. Air separation lifts light husk and dust away from the heavier kernels. The cleaned nuts are graded by diameter, so only a narrow size band continues to center use. This grading ensures the nut fits the wafer cavity without stressing the shell. Roasting develops aroma and reduces moisture, so the nut stays crisp inside the cream. Nuts enter a roaster with a controlled temperature curve that warms the nut evenly. Moisture is driven off gradually to avoid scorching the surface while the center remains raw. Roast endpoint is set by color and by moisture reduction because both affect crunch and oil behavior. After roasting, the nuts are cooled quickly, so residual heat does not soften wafer or thin the cream during assembly. Skin removal follows roasting because loose skin creates bitter notes and contaminates the nut coating stages. Nuts pass through rubbing rollers that loosen skins without crushing kernels. Aspirators pull the light skins away from the heavier nut stream. The nuts are screened again to remove broken pieces and fines. Whole nuts feed the center insertion system, while broken nuts feed paste and chopped nut streams. Chopped hazelnuts for the outer layer are produced from roasted kernels using calibrated cutting equipment. Cutting targets a consistent particle size that reads as crunchy pieces on the surface. Pieces that are too small become dust and reduce visual definition. Pieces that are too large create peaks that can shed or puncture the chocolate film. Screens remove fines and oversized fragments so the chopped nut bed remains uniform. The chopped nuts are held in dry conditioned air so they stay free-flowing. Hazelnut paste for the cream is produced from roasted nuts using staged grinding. Nuts are milled into a fluid paste where nut oil becomes the continuous phase. Temperature rises during grinding due to friction, so jackets and controlled throughput limit overheating. The paste is refined until particle size is below the gritty threshold. The finished paste is held in jacketed tanks with slow agitation to prevent oil separation. Wafer production runs as a dedicated stream because wafer structure must be crispy and low moisture. Flour is sifted to remove lumps and to standardize flow. Water and sugar are blended into a thin batter with controlled viscosity. Mixing is designed to hydrate flour without developing strong gluten. Batter is filtered to remove clumps that would create holes in wafer sheets. Wafer baking uses heated plates that cook the batter into a thin, porous sheet. The batter is deposited onto the plate and spread into a uniform film. Heat drives off water rapidly and sets the starch matrix. Bake time is tuned, so the sheet becomes dry and crisp without scorching. The sheet exits the plates and is cooled, so it becomes stable for forming. Forming converts wafer sheets into hemispherical shells with consistent thickness. Warm wafer is more pliable, so forming often occurs while the sheet still carries slight residual heat. A forming press pushes wafer into shaped cavities and trims edges to a clean rim. Rim quality matters because the seam must close without gaps. Formed halves are inspected for cracks because cracks lead to cream leakage and weak structure. Shell assembly joins two wafer halves into a hollow sphere. A thin ring of adhesive is applied to the rim of one half. The adhesive is typically a chocolate-based or fat-based compound that bonds quickly. The second half is aligned and pressed onto the first with controlled force. Too much force fractures wafer walls. Too little force leaves a pore seam that can open later. The joined spheres pass through a short cooling step, so the seam sets and the shell becomes rigid. Hazelnut cocoa cream is prepared as a fat continuous suspension that must be smooth and pumpable. Sugar and milk solids and cocoa solids are blended with hazelnut paste. Refining reduces particle size so the cream does not feel sandy. A mixing and conditioning step follows to distribute fat and reduce moisture. Temperature is controlled to reach a viscosity that can be dosed accurately into wafer shells. The cream is held in jacketed hoppers with gentle agitation to prevent separation and to keep a stable feed to depositors. Chocolate for coating is produced and tempered to a stable crystal form, so the shell sets with gloss and strength. Chocolate is melted and filtered to remove unmelted particles. Tempering cools and agitates the chocolate to create stable seed crystals. The chocolate is then brought to a working temperature where it flows well while retaining those seeds. Viscosity is checked because it determines coating thickness and nut adhesion behavior. Filling begins with dosing cream into the wafer sphere through a controlled opening. The depositor inserts a nozzle into the shell and dispenses a measured volume. The dose often coats the inner surface to create a bed that will hold the nut. This first dose must be large enough to anchor the nut and prevent rattling. It must not be so large that it blocks nut placement or overflows at sealing. Nut insertion uses a singulation system that feeds one nut per cycle. Nuts are oriented and delivered to a placement head. The head drops or presses the nut into the cream bed at a defined depth. Placement force is controlled because excessive force can crack the wafer or crush the nut. Centering is critical because an off-center nut creates uneven cream thickness and can shift mass distribution. A second cream dose fills the remaining cavity around the nut. The depositor dispenses cream in a way that avoids trapping air. Air pockets can collapse during cooling and create dents at the surface. Nozzle motion can trace a small pattern to wet the wafer interior evenly. The cream is leveled to a consistent height, so the closure step seals cleanly. The opening is sealed to contain the cream and stabilize the sphere for coating. Sealing can be done with a wafer plug or with a chocolate deposit, depending on the line design. A wafer plug is bonded with a thin layer of cream or compound. A chocolate plug is deposited and set quickly to create a barrier. The seal must be flush so the sphere rolls smoothly in the next stage. The filled spheres are cooled to firm the cream and strengthen handling stability. Cooling is staged so the cream fat network crystallizes without separating oil. The wafer must remain dry, so humidity control is important at this point. The spheres exit cooling with enough strength to pass through enrobing without deformation. Chocolate coating applies the layer that will carry the chopped hazelnuts. Spheres are conveyed through a chocolate curtain or a dipping system. Chocolate covers the surface and excess drains off on a wire belt. Vibrating sections help release trapped bubbles and smooth the film. Air knives can remove excess and define a consistent coating thickness. Thickness must be enough to bond nuts and provide bite. Thickness must not be so heavy that it obscures wafer crispness and slows cooling. Nut application happens immediately while the chocolate surface is still tacky. The spheres roll through a bed of chopped hazelnuts or receive a nut shower from above. Rolling ensures coverage reaches all sides of the sphere. Nut feed rate is tuned so coverage is dense and uniform. Too much nut feed causes clumps and uneven texture. Too little nut feed leaves bare patches that show through. Adhesion depends on the timing between coating and cooling. If chocolate sets too fast, nuts will not embed fully and will shed later. If chocolate sets too slowly, nuts can slide and create thin coverage zones. The process balances chocolate temper and curtain temperature with the distance to the cooling tunnel. The aim is a surface that stays tacky just long enough for nuts to lock in. Cooling tunnels solidify the outer chocolate and stabilize the internal cream. The first cooling zone sets the surface quickly so nuts stop moving. Subsequent zones pull heat out gradually to promote stable crystal growth and reduce contraction stress. If cooling is too aggressive, the chocolate can crack around nut peaks. If cooling is too gentle, the coating remains soft and can scuff during wrapping. As cooling proceeds, the cream inside also equilibrates and becomes firmer. This improves bite definition and reduces oil migration. The wafer remains protected because the chocolate and cream act as moisture barriers. Final exit temperature is set, so the sphere is hard enough to handle while avoiding condensation when it enters ambient packaging areas. A Mars bar is manufactured by producing an aerated nougat core, layering it with a cooked caramel sheet, enrobing the assembled slab in tempered chocolate, then cooling and wrapping while thickness and weight remain tightly controlled. Production starts with staging sugar and syrups, because nougat and caramel both depend on precise solids. Granulated sugar is screened to remove lumps and to control crystal size. Glucose syrup is held in jacketed tanks so viscosity stays stable for pumping. Water is filtered and tempered so dissolution and cooking are consistent. Milk powders and cocoa powders are sieved to remove clods that would create specks. Fats are melted and filtered because clean fat flow is needed for accurate dosing. Nougat production begins with cooking a syrup to a target concentration. Sugar, glucose syrup, and water are metered into a cooker and heated to drive off water. Temperature and residence time define final solids, and therefore nougat chew. If the syrup is undercooked, the nougat stays soft and can slump during assembly. If overcooked, it becomes tough and brittle after cooling. The cooked syrup leaves the hot zone and is delivered to the whipping stage at a controlled temperature. In parallel, a protein phase is prepared to create the aerated structure. A solution based on egg albumin or a similar foaming protein is mixed to a defined concentration. The solution enters a continuous aerator that whips it with controlled shear. Air is metered into the aerator, so bubble size and density remain stable. The foam density is monitored because it sets nougat lightness and final bar weight. The hot syrup stream and the foam stream meet in a continuous mixer. Mixing must be strong enough to distribute syrup through foam without collapsing bubbles. As hot syrup contacts foam, it partially cooks proteins and strengthens bubble walls. This locks in a stable microcell structure. Fat can be injected during this stage to soften bite and reduce stickiness. Fat dosing is controlled because it changes both texture and how the nougat behaves under cutters. Flavor and cocoa notes are introduced during the nougat mixing stage, depending on recipe. Additions are made after the highest heat exposure, so aromatics are preserved. Emulsifiers can be added in small amounts to stabilize the air-fat sugar system and improve flow. The mixed nougat exits as a warm plastic mass with controlled density. Nougat is deposited onto a moving belt as a continuous slab. A depositor spreads it to a defined width. Gauge rollers and leveling bars set thickness. Thickness control matters because the nougat layer sets the bar cross section and influences cooling time. The slab then enters a cooling tunnel where temperature drops gradually. Cooling firms the nougat and stabilizes the aerated structure without creating large internal stress. Caramel production runs as a separate stream because it requires a different cook profile. Sugar and glucose syrup are cooked with milk components to create a chewy caramel with controlled solids. Heating develops color and flavor by controlled browning while driving off water. Fat is added to smooth texture and reduce stickiness. The cook endpoint is set, so caramel is elastic and does not flow at room temperature. After cooking, caramel is cooled to a workable temperature and held in a jacketed tank. Gentle agitation prevents skin formation and keeps temperature uniform. Caramel viscosity must be stable for sheet forming. If too hot, it runs and makes thin spots. If too cool, it tears and creates ridges. Caramel is applied over the nougat slab as a continuous layer. A slot depositor or spreader head lays down a ribbon and spreads it across the width. A leveling station sets thickness and smooths the surface. The caramel layer must bond to nougat without sinking. Bonding depends on the temperature difference between the layers. If caramel is too hot, it can melt the nougat surface. If too cool, it will not fuse and may delaminate later. Once layered, the combined slab is cooled again. Cooling firms the caramel and strengthens the interface. Cooling is staged so caramel surface sets without cracking. A stable interface is important because the slab will be cut and then exposed to chocolate curtain forces during enrobing. The slab then moves to sizing and cutting. Edge trimming removes uneven edges and returns trim to rework streams under controlled ratios. The main slab is cut into long ropes using rotary knives. Rope width defines bar width. A cross cutter then cuts ropes into bar lengths. Cutter timing is synchronized with belt speed so weight remains consistent. Knife temperature and coatings are managed because caramel can stick and smear. Clean cuts prevent drag marks that would show through chocolate. Bars are transferred onto an enrobing line with controlled spacing. Transfer must avoid deforming nougat and caramel layers. Spacing ensures chocolate can flow around each bar without bridging. Bars may pass through a brief pre-chill to firm surfaces and improve chocolate coverage. Chocolate preparation is managed carefully because coating quality depends on temper. Chocolate is melted and filtered. It is tempered to create stable seed crystals that yield gloss and snap. Working temperature is held in a narrow range, so viscosity stays stable. Viscosity determines coating thickness and therefore final weight and bite. Enrobing coats each bar in chocolate. Bars pass through a chocolate curtain that covers the top and sides. The underside is coated by a bottoming system or by curtain wraparound. Excess chocolate drains through a wire belt. Air knives remove excess and smooth the surface. Air knife settings influence edge definition and foot thickness. Proper control prevents heavy feet and exposed corners. If a top pattern is used, a stringer applies thin lines of chocolate across the surface. The stringer must be synchronized with bar speed and chocolate viscosity. Pattern lines must bond before the base coat sets fully. The bars then enter the cooling tunnel immediately. Cooling sets the chocolate and stabilizes the final bar. The first zone sets the surface quickly so the coat does not slump. Subsequent zones cool more gradually to promote stable crystal growth and reduce bloom risk. Cooling also brings the internal nougat and caramel to a stable temperature. If bars exit too warm, the coating can scuff in wrapping. If too cold, the coating can crack under wrapper folds. Hershey's. Chocolate is manufactured by converting cocoa and dairy ingredients into a stable fat-based suspension, refining it to a smooth particle size, conching to stabilize flavor and flow, tempering to control cocoa butter crystals, then molding and packaging the finished pieces while temperature and viscosity remain tightly controlled. Production starts with raw ingredient preparation because chocolate texture depends on moisture and particle behavior. Sugar is stored dry and screened to remove clumps and control crystal size. Milk ingredients such as milk powder are stored under low humidity and sieved to break agglomerates. Cocoa powder and cocoa liquor components are prepared as clean streams with controlled fat content. Cocoa butter is melted in jacketed tanks and filtered so it can be metered precisely. Emulsifiers and flavor additions are staged as low-dose liquids or powders for later addition. Cocoa inputs can come as cocoa liquor and cocoa powder, rather than on-site being. Processing in many large-scale lines. Cocoa liquor is held warm so it stays fluid. It is filtered to remove solid lumps. Cocoa powder is sifted to remove compacted clods because clods do not refine evenly and can create specks. All cocoa streams are kept dry because water causes chocolate to thicken rapidly and lose flow. The first assembly step creates a pre-mixed chocolate mass. Melted cocoa butter and cocoa liquor form the fat continuous base in a mixer. Sugar and milk powders are added gradually, so each particle becomes wetted by fat rather than remaining as dry islands. Mixing uses strong folding and wall scraping to prevent buildup. The objective is a uniform paste where dry particles are distributed evenly through the fat phase. In some milk chocolate processes, the dairy and sugar can be developed through a crumb-style step that alters flavor and texture. In that approach, milk and sugar are combined and cooked to drive off water and create a dry crumb material. The crumb is then milled and blended with cocoa components and fats. Whether a crumb step is used or not, the downstream refining and conching steps still determine final smoothness and flow. Refining is the main texture forming step. The mixed paste contains sugar and milk and cocoa particles that are still too large for smooth eating. Refining reduces these particles to a small size so they cannot be detected on the tongue. A common method uses a series of rollers with decreasing gaps. The paste is fed through the roll refiner and is squeezed and sheared. Particle size drops with each pass. The output leaves the final roll as thin flakes or ribbons. Refined flakes have high surface area and are not yet coated fully with free fat. They can also carry small amounts of moisture and trapped air. These factors make the mass behave dry and pasty. The next step, conching, converts this into a smooth flowing chocolate by coating every particle and driving off moisture and volatiles. Conching is performed in a vessel with paddles or rotors that knead the chocolate under controlled heat. Heat keeps cocoa butter fluid and allows particles to be coated. Mechanical work breaks down remaining agglomerates and distributes fat uniformly. Venting and airflow remove moisture and sharp volatiles. Moisture control is critical because even a small water content can cause thickening. Conching, therefore, holds temperature and airflow, so water leaves gradually without overheating. During early conching, the mass may be relatively dry and crumbly. As work continues and fat coats surfaces, the mass becomes smoother and flows more readily. This is the point where viscosity becomes stable enough for pumping. Conching time is tuned to reach the desired balance between flavor smoothing and rheology. Under conching leaves harsh notes and higher viscosity. Over conching can strip aromatics and reduce throughput. Emulsifiers are typically added late in conching to fine-tune flow. Lecithin reduces yield stress by improving particle wetting. Another emulsifier can be used to reduce viscosity further. These additions allow the chocolate to flow through pumps and depositors at lower fat content or with more stable behavior. Emulsifier dosing is tightly controlled because small changes can make chocolate too thin or too thick for molding. After conching, the chocolate is transferred to storage tanks that maintain temperature. Tanks use gentle agitation to keep the suspension uniform and prevent separation. Filters remove any foreign particles or unmelted lumps before tempering. At this stage, the chocolate is finished in texture and flavor, but its cocoa butter crystals are not yet in the correct state for molding. Tempering is the controlled crystallization step that gives chocolate snap and gloss and stable shelf behavior. Cocoa butter can crystallize in several forms, and only one main form gives the desired contraction and shine. Tempering creates stable seed crystals and then maintains the chocolate at a working temperature where these seeds remain while unstable crystals melt. Continuous tempering machines heat the chocolate to melt all existing crystals. They then cool it while agitating so crystals begin forming. They then reheat slightly to melt unstable forms while leaving stable seeds. The output is a chocolate that flows well but contains the correct seeds to set quickly. Temper is monitored by temperature and by viscosity signals and by tempermeters that measure crystal content. Once tempered, the chocolate is ready for shaping. For bars and kisses and similar pieces, molding is common. Polycarbonate or metal molds travel under deposit heads. The depositors meter a precise mass into each cavity. Vibration follows immediately. Vibration removes trapped air bubbles and levels the surface. It also helps chocolate fill sharp corners and improves surface gloss. Cooling sets the molded chocolate. Molds enter a cooling tunnel with staged zones. Early. Zones cool the surface quickly so the chocolate skin forms and holds shape. Later zones cool more gradually so the interior solidifies with stable crystals. The cooling profile is tuned so chocolate contracts and releases from the mold. Too rapid cooling can create stress and cause cracking or bloom later. Too slow cooling reduces throughput and can soften detail. After cooling, the pieces are demolded. Molds are flexed or tapped and the chocolate releases due to contraction. The pieces transfer to conveyors that handle them gently to prevent scuffing. Inspection checks can detect missing fill or broken corners. Weight checks confirm deposit accuracy. Reject systems divert defects to rework. If inclusions are used, the process adds an inclusion dosing step. Nuts or crisp pieces are screened to a tight band and kept dry. Inclusions can be mixed into chocolate before depositing or placed into molds before filling. Mixing into chocolate requires controlling suspension, so inclusions do not settle. Placing into molds requires accurate dosing, so count is consistent. Inclusions increase cooling time because they change heat capacity and can create local thick regions. For filled products, the process uses stage depositing. A shell is deposited first and partially set. A filling is deposited and then capped with chocolate. Shell thickness and sealing quality must be controlled to prevent leakage. Cooling profiles are adjusted because the filling can insulate and slow set. After demolding the chocolate pieces, move to packaging. Packaging must protect chocolate from moisture and oxygen and physical abrasion. Pieces feed into wrapping machines that form foil or film around each unit. Wrapping tension and fold geometry are controlled, so the wrap conforms without scuffing. Heat sealing is used for film wraps, while crimping is used for foil wraps depending on format. Coded information is applied during packaging by inkjet or laser. Vision systems confirm code presence and wrapper alignment. Metal detection can be used as a final integrity check. Wrapped units are collated into bags or cartons. Bagging users form fill-seal systems that drop wrapped units into film tubes and seal them. Cartoning erects cartons and inserts a defined count. Nerds are manufactured by cooking a high solid sugar syrup, setting it into a brittle glass, fracturing that glass, into tiny irregular pieces, then sorting and finishing those pieces so they stay crunchy and free-flowing in the package. Production starts with preparing the main carbohydrate streams because the final crunch depends on solids and crystallization control. Granulated sugar is screened to control crystal size and remove dust that can scorch during cooking. Corn syrup is stored in jacketed tanks, so viscosity stays stable for pumping and metering. Water is filtered and tempered because inlet temperature affects dissolution. And cook consistency. Acid powders and salt are staged in microfeeders because small changes shift flavor intensity. Flavor concentrates and colors are prepared in separate tanks, so each can be dosed precisely. The first operation is dissolving and syrup formation. Sugar and water enter a dissolver where agitation prevents settling and speeds dissolution. The goal is a clear solution with no undissolved grains because grains concede unwanted crystallization later. The solution passes through strainers to remove stray solids that would create localized graining. Corn syrup is blended in to inhibit crystallization and to control viscosity as the syrup concentrates. Syrup cooking raises solids to the level needed for a brittle candy glass. Cooking is done in continuous coils or batch kettles, depending on capacity. In a continuous system, the syrup is pumped through a heated coil under pressure so it can reach high temperature without boiling. After the heating zone, the syrup enters a flash stage where pressure drops and water vapor is released rapidly. This step fine-tunes final moisture and stabilizes the syrup at the target solids. Final moisture is the key parameter because it determines how the sheet fractures. Too much moisture produces a tough candy that bends and breaks into large chunks. Too little moisture produces an overly brittle candy that shatters into dust. Temperature and residence time are therefore controlled tightly. Inline density measurement and temperature measurement are used as proxies for solids. Flow control keeps residence time stable, so every portion of syrup receives the same heat history. After cooking, the syrup is cooled to protect sensitive additions and to set the right viscosity for casting. Cooling is done with heat exchangers that drop temperature along a controlled curve. Acid addition is often delayed until after this cooling because high heat can accelerate sucrose inversion and change texture. When the syrup reaches the blending temperature, acids are injected as solutions for rapid dispersion. The acid level sets the tartness and also influences shelf stability by affecting water activity behavior. Flavor and color are added late to preserve aroma. Oil-based flavors are introduced through precision pumps into a turbulent section and mixed with static mixers. Colors are introduced as concentrated solutions and blended until uniform. Nerds commonly use multiple colors and flavors, so the line splits into parallel streams after the cook. Each stream receives its own color and flavor dosing and then proceeds through identical casting and breaking equipment. Separating streams prevents cross-tint and allows each flavor to target its own acid balance. Casting converts liquid candy into a solid glass that can be fractured. The hot syrup is deposited onto a moving steel belt or onto casting trays as a thin sheet. Deposit rate and belt speed set sheet thickness. Thickness is important because it affects cooling rate and fracture size. A thicker sheet cools slower and can form internal stress gradients. A thinner sheet cools quickly and can become too brittle at the surface. Cooling begins immediately after casting. Cooling plates under the belt pull heat out evenly. Air above the sheet can be controlled to prevent moisture pickup and to manage surface set. The goal is to transition the syrup from a viscous liquid into an amorphous glass without large crystal growth. Large crystals would create a gritty texture and weaken control of fracture. Rapid controlled cooling helps keep the structure glassy. Some lines introduce controlled stress features to guide fracture. The sheet can pass over rollers that flex it slightly. Flexing creates micro cracks and stress lines that encourage predictable break patterns. Scoring can also be used where shallow grooves are pressed into the sheet. Grooves act as crack initiators and reduce random oversized pieces. Once the sheet reaches the target brittleness, it is lifted from the belt and fed into a primary breaker. The breaker cracks the sheet into chips using toothed rollers or oscillating bars. The first break is staged and aims to create manageable chips rather than final nerd size. Staged breaking reduces dust creation because each stage applies controlled energy rather than a single violent shatter. Chips then move into a secondary crushing system that brings size down to the final granule range. Roll crushers are common because they apply compressive force that produces angular pieces. Roll gap controls the size distribution. A tight gap creates more fines. A wide gap leaves more oversize. Roll speed and feed rate are tuned to keep the crushing stable and prevent surges that create inconsistent size. After crushing, the material enters screening and classification. Vibratory screens separate into fractions in a single pass. The target fraction becomes product stream. Oversize is returned to the crusher for another pass. Fines are separated because they create dust and can clump. Fines can be recycled in controlled amounts depending on the process because fines affect flow and dissolution. Particle shape is intentionally irregular because it creates the characteristic crunchy mouthfeel. The process therefore avoids rounding steps that would polish edges. At the same time, it controls sharp spikes because spikes can fracture later and increase dust. Crusher settings and screen selection balance angularity with durability. Each color stream goes through its own crushing and screening loop. This keeps recycle streams color pure and prevents shade drift. It also allows each flavor stream to be tuned for its own brittleness. Different acid and flavor loads can change glass fragility, so crusher settings may vary slightly by stream. After sizing the granules, enter conditioning bins. Conditioning allows internal moisture to equalize within each piece. Even small moisture gradients can cause caking in storage. Conditioning also stabilizes crunch by keeping the glass phase below its transition point. Air in the bins is controlled for humidity. Too humid air causes surface tack and clumping. Too dry air can increase brittleness and create fines during conveying. At this stage, a light finishing step can be used to improve flow. A tiny amount of anti-caking agent can be applied as a dust in a tumbler. The goal is to reduce surface adhesion points without changing taste. Distribution is controlled so the finish is uniform. Excess dust is removed by aspiration so the product remains clean. For stronger sour perception, the process can place some acid at the surface rather than fully in the body. Surface loading is done by misting a very small amount of binder and then applying a fine acid sugar blend. Drying follows immediately, so pieces do not fuse. This method increases immediate sour hit because surface acids dissolve first. It also requires strict humidity control because acids can attract moisture. When the product format calls for 2 flavors in one package, the streams are blended after they are fully sized and conditioned. Blending uses gravimetric feeders that meter each color stream to a defined ratio. The blended stream enters a gentle blender that mixes without crushing. Paddle designs lift and fold rather than grind. Mixing time is short because long mixing can create fines by abrasion. The blended product is sampled to confirm ratio and color distribution. Color ratio stability is important because consumers expect a consistent mix. Sampling also checks bulk density and flow. Bulk density affects how packaging machines dose by volume. Flow affects how smoothly the product runs through hoppers and weighers. Conveying to packaging is designed to limit breakage. Drop heights are minimized. Chutes use smooth surfaces and shallow angles. Pneumatic conveying can create fines if velocity is high, so low velocity, dense phase systems are preferred when used. Transfer points can include dust extraction to remove loose fines. Butterfinger is manufactured by building a crisp layered peanut candy core through staged cooking and lamination, then coating that core in chocolate and packing it after controlled cooling. Production begins with staging peanuts and the main sugar syrups because the final brittle texture depends on solids and oil balance. Roasted peanuts arrive as whole kernels and are screened to remove fines and shell fragments. The kernels are graded so size and moisture stay consistent. A portion of peanuts is milled into peanut butter or peanut paste that will act as the fat phase for the candy core. Milling is done in staged grinders that reduce particle size while temperature is controlled to prevent oil separation. In parallel, the syrup system is prepared as the structural backbone. Granulated sugar is screened to remove clumps and control crystal size. Corn syrup is held in jacketed tanks, so viscosity stays stable for metering. Water is filtered and tempered, so dissolving and cooking repeat reliably. Salt and emulsifiers are staged in microfeeders because small changes shift bite and brittleness. Syrup cooking starts in a dissolver where sugar and water are mixed until the solution is clear. The clear solution feeds a cooker that drives off water and raises solids. Corn syrup is injected to reduce uncontrolled crystallization and to tune viscosity. Temperature and residence time are controlled because they set the glass transition behavior of the finished candy. Once the syrup reaches a target concentration, it is discharged to a cooling section. Cooling reduces temperature to a window where peanut paste can be blended without scorching oils. The syrup remains hot enough to stay fluid and to wet dry surfaces during mixing. The blend point is chosen to keep the mixture workable while avoiding excessive moisture pickup. Peanut paste is prepared to a defined fat content and then delivered to the mixer at a stable temperature. If the paste is too cold, it stiffens and resists blending. If the paste is too warm, it thins and can separate under shear. The paste temperature is managed with jacketed lines and gentle agitation. The syrup and peanut paste meet in a high torque mixer that can handle rapid viscosity changes. The mixer folds the syrup into the paste and distributes fat through the sugar matrix. The mixture shifts from glossy liquid to a thick plastic mass as it cools. This stage determines how the candy will form layers later. Too much mixing energy creates an overly uniform matrix that loses flake. Too little mixing leaves fat streaks that weaken structure. A controlled crystallization phase is used to create the brittle layered character rather than a smooth, toffee-like body. The mass is moved through working rollers, or a puller that stretches and folds it repeatedly. Each fold creates thin strata of sugar phase and peanut solids. As the strata cool, they set into a stack that fractures into crisp flakes when bitten. Working conditions are tuned to balance plasticity and set speed. If the mass is too hot, it flows, and the layers collapse into a dense block. If the mass is too cool, it cracks during folding and sheds crumbs. The line holds a narrow temperature band, so the mass can be laminated without tearing. During working, the system also manages air content. Small controlled voids can enhance crisp fracture and lighten density. Excess air creates weak planes that break during enrobing and packaging. The working equipment compresses the mass to remove large bubbles while maintaining fine structure. As the laminated mass develops, it is formed into a continuous slab or rope. A sheeter can spread it to a defined thickness for bar production. A rope former can create a continuous strip that will be cut later. Forming must preserve layers, so high pressure extrusion is avoided when flake is the goal. Thickness control is critical because it affects both bite and coating ratio. The slab passes under gauge rollers that set height within tight limits. Edge guides maintain width so cutters can portion accurately. Scrap at the edges is trimmed and routed to rework streams in controlled ratios. Cooling follows, forming to lock the layered structure before cutting. Cooling is staged so the surface sets without forming a hard shell around a warm interior. A hard shell can trap heat and cause internal delamination later. A gradual profile brings the entire slab to a stable cut temperature. Cutting converts the slab into individual cores. Rotary knives or guillotine cutters slice long strips and then cross-cut them into bar lengths. Cutter timing is synchronized with belt speed to maintain consistent weight. Blade coatings and temperature control reduce sticking from peanut oils. Clean cuts preserve sharp edges that help chocolate adhesion. The cut cores are fragile and can chip if handled roughly. Transfer systems use short drops and soft transitions. Spacing belts separate cores so chocolate can wrap each piece without bridges. Any broken pieces are screened out because they shed crumbs in chocolate. Chocolate preparation runs as a separate stream because the coating must set with gloss and resistance to bloom. Chocolate is melted in jacketed tanks and filtered to remove unmelted particles. Tempering then establishes stable cocoa butter crystals for a clean snap. Working temperature is held tightly because viscosity determines coating thickness. Enrobing applies chocolate to the cores in a continuous curtain. Cores pass through the curtain and receive top and side coverage. A bottoming section coats the underside through a chocolate bath or a secondary curtain. Excess chocolate drains through a wire belt, so thickness remains consistent. Air knives smooth the surface and define the foot at the base. Coating thickness must be balanced against the brittle core. Too thick a coat makes the bar heavy and slows set time. Too thin a coat exposes edges and increases scuffing. Curtain height and chocolate flow rate control the deposited mass. Belt speed and air knife pressure fine-tune the final profile. Because the core sheds fine crumbs, the enrober includes crumb management. The line screens cores before coating to reduce loose fragments. The chocolate bath is filtered and recirculated to remove crumb carryover. Stable filtration prevents burnt fragments and keeps the surface smooth. After enrobing the bars, enter a cooling tunnel that sets the chocolate coat. The first zone sets the surface quickly so the coating does not slump. Later, zones cool more gradually so stable crystals grow without stress. Cooling too fast can crack chocolate around sharp core corners. Cooling too slow can leave a soft coat that scuffs in wrapping. During cooling, the peanut candy core also equilibrates. Residual heat migrates out and moisture gradients flatten. The layered core must remain dry to keep its crisp. Fracture. Tunnel humidity is controlled, so the core does not absorb moisture through micro cracks. The chocolate coat acts as a barrier once fully set. If the product uses a top pattern or drizzle, it is applied before the main set completes. A stringer deposits thin lines of chocolate across the surface. The drizzle bonds to the base coat while it is still tacky. The bars then continue through cooling, so both layers crystallize together. Once the bars exit cooling, they are inspected for coating coverage and shape. Vision systems detect exposed edges and broken corners. Weight checks confirm portion control from cutting and coating. Bars outside tolerance are diverted to rework streams. Rework is managed carefully because brittle core fragments behave differently than fresh slab. Wrapping begins after the chocolate reaches a stable handling temperature. Bars feed into flow wrappers that form film around each unit and seal it. Seal jaws apply heat and pressure for a defined dwell. Film tension is controlled to avoid scuffing the chocolate surface. Wrapper timing keeps seals away from crumbs that could interfere with closure. For multi-packs, bars are collated into groups and over-wrapped or cartoned. Collation uses lane gates that maintain spacing without impact. Overwrap film is sealed around the group. Cartons are erected and loaded with pushers that avoid crushing. Finished units are then case-packed and palletized. Milky Way begins with air management because the bar's defining texture is an aerated center that must hold millions of microbubbles through cutting, enrobing, and packaging without collapsing. The aerated center is built from a cooked sugar syrup and a stabilized protein phase that can trap air reliably. Sugar is handled as an engineered solid. It is screened so crystal size is consistent and so clumps do not enter the cooker. Glucose syrup is stored warm in jacketed tanks so it meters smoothly and maintains stable viscosity. Water is filtered and tempered because inlet temperature changes dissolution speed and cook behavior. Milk-derived powders are kept dry and sieved to remove agglomerates because lumps create gritty spots and viscosity spikes. Fat streams are melted and filtered because small solids can disrupt pumps and depositors. Syrup cooking sets the solid's foundation for the nougat. Sugar, glucose syrup, and water are metered into a cooker and heated to drive off water. The cook is controlled by temperature and residence time because those define final moisture. If moisture is high, the nougat stays soft and can deform under cutters. If moisture is low, the nougat becomes tough and loses its light bite. The cooked syrup exits the hottest zone and is conditioned to a temperature that will strengthen foam without scorching it. In parallel, the foaming phase is prepared. A protein solution is mixed to a defined concentration and then fed to a continuous aerator. The aerator meters air into the stream and whips it into fine bubbles. Bubble size distribution matters because large bubbles collapse during later handling and create voids. Small bubbles create a smooth, uniform bite and stable density. Aeration is controlled by rotor speed, airflow rate, and back pressure. Density is monitored continuously because it is the main lever that determines bar weight and bite. The hot syrup stream and the foam stream meet in a high-capacity, continuous mixer. The mixer must blend quickly without stripping the foam. The hot syrup partially cooks and strengthens the protein films around bubbles. This locks in the microcell structure. Mixing elements are designed to fold rather than beat, because beating breaks bubbles. At this stage, fat is injected as a thin stream to soften texture and reduce stickiness. The fat must disperse without destabilizing the foam. Emulsifiers can be added in small doses to improve stability and to keep the matrix smooth as it cools. Once the nougat reaches the target density, it is formed into a continuous slab. A depositor spreads the aerated mass onto a moving belt. Leveling bars and gauge rollers set thickness. Thickness is held within tight limits because it sets the cross-section and affects cooling time. The slab enters a cooling tunnel where temperature drops in stages. Stage cooling prevents a hard skin from forming while the interior remains warm. The aim is an even set that keeps the air cell structure intact. Some Milky Way formats add caramel as a second layer. Caramel production runs as its own stream because it requires a different cook profile and different rheology. Sugar and glucose syrup are cooked with milk components to develop caramel notes and to reach an elastic solids endpoint. Fat is added to smooth the caramel and reduce tack. The endpoint is chosen, so caramel holds its shape as a sheet but still bites cleanly. If caramel is too soft, it flows and squeezes during cutting. If too firm, it fractures and creates edge cracks under chocolate. Caramel is cooled to a deposit temperature that remains spreadable. It is held in a jacketed tank with gentle agitation to prevent surface skin. From there, it feeds a slot depositor that lays a continuous ribbon over the nougat slab. A leveling station spreads it to uniform thickness. The interface between nougat and caramel is controlled by temperature. The nougat must be firm enough to support caramel without compression. The caramel must be warm enough to bond, but not so warm that it melts the nougat surface. After layering, the combined slab goes through another conditioning zone. This zone firms the caramel and stabilizes the interface. Cooling is staged to avoid creating stress between layers because they contract at different rates. A stable interface is essential because the slab will be cut into bars and then exposed to chocolate curtain forces during enrobing. Cutting turns the slab into individual centers with consistent mass. Edge trimming removes uneven edges and returns trim to controlled rework streams. The main slab is cut into long lanes with rotary knives. A cross cutter then slices lanes into bar lengths. Timing is synchronized with belt speed, so every piece has the same length. Knife surfaces are managed to reduce sticking. The objective is clean edges with minimal smear because smear shows through chocolate and causes coating defects. The cut centers are transferred to the enrobing line with controlled spacing. Spacing prevents bars from bridging under the chocolate curtain. Transfer points are designed to avoid compression because aerated nougat can dent. A brief pre-chill can be used to firm surfaces. Firmer surfaces accept chocolate more evenly and reduce flotation in the curtain. Chocolate coating begins with chocolate conditioning and tempering. Chocolate is melted and filtered and then tempered to create stable cocoa butter seed crystals. Tempering is essential because the coating must set with gloss and resist bloom. Working temperature is held tightly because viscosity determines curtain thickness. A stable curtain is critical because coating thickness affects final weight and cooling time. Enrobing applies chocolate in a continuous curtain that coats the top and sides. Bottom coating is added by a bottoming system that deposits chocolate under the bar. Excess drains through a wire belt. Air knives smooth the surface and control the foot. Air knife settings must be tuned because too much air exposes corners and too little air leaves a heavy foot that can crack during cooling. If a top drizzle is used, it is applied immediately after the main curtain. A stringer deposits thin lines across the surface. The drizzle must bond before the base coat fully sets. Flow and timing are synchronized with belt speed so the pattern stays consistent. The coated bars enter a cooling tunnel that sets the chocolate. The first zone sets the surface quickly so the coat does not slump or smear. The next zones cool more gradually so stable crystals grow without creating stress cracks. Tunnel humidity is controlled to prevent condensation because condensation can cause sugar bloom on the surface. The bars exit cooling at a temperature where the chocolate is hard enough for wrapping and the center is stable. During cooling, the nougat and caramel continue to equilibrate. The aerated matrix firms as fats crystallize and moisture redistributes slightly. The caramel reaches its final elasticity. The chocolate coat becomes a barrier that slows moisture exchange and protects texture over shelf life. Inspection steps typically occur after cooling. Weight checks confirm portion control. Vision systems can detect exposed edges and surface defects. Bars with coating misses or broken corners are diverted. Diverted product is handled carefully because rework streams must not overload the chocolate system with unstable crystal history. Wrapping begins once the chocolate is fully set. Bars enter flow. Wrappers that form film around each bar and heat seal it. Seal jaws apply temperature and pressure for a defined dwell time. Film tension is controlled so it does not scuff the chocolate surface. Registration controls align printed film with bar position. Coating is applied for traceability. A thick ribbon of semi-frozen ice cream drops into a paperboard pint, while a dark swirl and solid chunks enter the same moving stream. The product is cold enough to hold suspended pieces, but still soft enough to flow. Inside the filling nozzle, smooth ice cream, sauce, and inclusions are brought together only moments before the pint is filled. This prevents the swirl from disappearing into the base and keeps the chunks distributed through the container. For a Ben & Jerry's chunk and swirl flavor, several production streams must arrive at this point in exact condition. The ice cream base must be pasteurized, chilled, aged, flavored, and partially frozen. The sauce must be thick and pumpable. The chunks must be cold, correctly sized, and free-flowing. The empty pint cups must be formed, printed, clean, and positioned beneath the filler. The ice cream base begins with dairy ingredients entering stainless steel blend tanks. Milk and cream flow through metered pipes. Sugar enters as a measured dry or liquid stream. Milk solids, egg ingredients for custard-style formulas, stabilizers, emulsifiers, cocoa, vanilla, or other flavor-based ingredients are added according to the specific variety being produced. Agitators rotate inside the tank, creating a continuous circulation. Dry powders fall into the liquid and disappear as they hydrate. Cream disperses through the milk phase. Sugar dissolves. The mixture becomes smooth and uniform, with its fat, water, sugar, and solids distributed evenly through the tank. Some flavors begin with a pale cream base. Others receive cocoa or another blended ingredient that immediately changes the liquid color. A chocolate base turns from off-white to deep brown as the powder is fully wetted and dispersed. The tank keeps moving until no streaks remain. The blended base then enters a pasteurization system. Pumps push the liquid through a heat exchanger where thin metal plates separate the ice cream mix from a heating medium. Heat transfers rapidly into the product. The base reaches its required treatment temperature while staying enclosed inside the process line. After the heating section, the warm base passes into homogenization equipment. Homogenization changes the structure of the fat in the mixture. The liquid is forced through extremely narrow openings under high pressure. Larger fat droplets break into much smaller droplets and spread evenly throughout the base. This step gives the finished ice cream a smoother, more stable body. Without it, fat could gather unevenly, and the frozen texture would become coarse or greasy. The homogenized base leaves the machine as a consistent liquid, ready for rapid cooling. The hot base immediately enters another heat exchange section. Chilled fluid on the opposite side of the plates pulls heat away quickly. The ice cream mix drops to a low refrigerated temperature while remaining liquid. The chilled base moves into aging tanks. These tanks are jacketed with cooling systems and fitted with slow agitators. The mixture rests cold while fat partially crystallizes and stabilizing ingredients finish hydrating. The liquid becomes slightly thicker and more capable of trapping air during freezing. While the base is aging, the chunks are prepared on a separate line. In a cookie dough flavor, flour-based dough ingredients, sugar, fat, flavoring, and chocolate pieces are mixed into a thick mass. The dough is rolled, extruded, or sheeted, then cut into small pieces, sized to travel through pumps, feeders, and filling nozzles. In a brownie-style flavor, a dense baked slab is produced from batter, baked until set, cooled thoroughly, and cut into cubes or irregular chunks. In a chocolate piece flavor, tempered chocolate is shaped, cooled, broken, and screened into pieces of the required dimensions. Every inclusion must be cold before it reaches the ice cream stream. Warm pieces would soften the semi-frozen base and disturb the freezing balance. The chunks pass through cooling or freezing equipment, then through screens that remove excessive crumbs, oversized pieces, or clusters joined together. The swirl follows another path. A caramel, chocolate, fruit, cookie, or nut-based sauce is mixed in heated kettles or blending tanks. Sugar syrups, flavor ingredients, fats, cocoa, fruit preparations, or other components are heated and agitated until the sauce reaches a smooth, even texture. The sauce is then cooled to a controlled pumping temperature. It must be fluid enough to travel through pipes and dosing pumps, but thick enough to remain in visible ribbons inside the ice cream. If the swirl is too thin, it spreads through the base. If it is too thick, the depositor cannot create clean bands. Once the aged ice cream base reaches the correct condition, it moves toward the continuous freezer. Flavor additions that belong throughout the base are introduced before or during this stage. Vanilla, chocolate, fruit base, coffee concentrate, or other liquid flavor components disperse evenly through the chilled mix. Inside the continuous freezer, the liquid base meets a refrigerated barrel. Rotating scraper blades sweep frozen material from the inner wall as it forms. The base freezes rapidly against the cold surface, and the blades continuously fold those tiny ice crystals back into the moving product. Air is incorporated during freezing in a controlled amount. The mixture expands slightly as minute air cells spread through it. The developing ice cream changes from a chilled liquid into a thick, soft, extrudable mass. The crystals remain small because the freezing and scraping occur quickly. The freezer does not harden the product completely. Fully hardened ice cream would not flow through the filling system. It leaves the barrel at a soft frozen consistency, similar to a dense flowing paste, capable of holding chunks without letting them sink immediately. The semi-frozen base reaches the inclusion feeder. Chilled chunks are delivered from a hopper through measured gates or rotating feed equipment. The mechanism spaces the pieces into the ice cream stream rather than releasing them in clumps. The moving base captures each inclusion and carries it forward. The chunk-loaded ice cream then reaches the swirl injector. Pumps deliver the prepared sauce through narrow lines into the product stream. The sauce is not aggressively mixed. Instead, it is introduced in controlled folds or ribbons, leaving distinct streaks that remain visible after the pint is opened. Empty pint containers arrive at the filling carousel or indexing conveyor. The containers are formed from coated paperboard with printed outer surfaces and a moisture-resistant inner barrier. They feed from stacked magazines, separating one at a time and dropping into holders with open tops facing upward. Each pint advances beneath the filling head. The nozzle lowers or aligns above the opening. A measured charge of ice cream enters the cup, bringing chunks and swirl with it. The thick product folds into the container, filling from the bottom upward while preserving streaks and suspended pieces. The fill quantity is controlled carefully. Too little product leaves excess empty space. Too much interferes with clean lid application. The filler stops at the target amount, and the filled pint moves to the top finishing section. A surface leveling mechanism may lightly settle the upper layer without blending the pattern away. The top must remain even enough to accept a lid, while the product beneath it keeps its irregular distribution of ice cream, chunks, and sauce. Lids are supplied from a magazine and separated individually. Each lid drops or presses onto the rim of a filled pint. The closure engages with the cup edge, forming a covered container, ready for hardening. Coating equipment applies production marks to the lid, cup base, or printed outer surface as the pint continues along the line. At this moment, the ice cream is packaged, but still soft inside. The pints enter a hardening tunnel or spiral freezer. Extremely cold, circulating air moves around every container. Heat is pulled from the ice cream through the cup walls and lid area. The soft frozen mass becomes rigid as more water freezes. Chunks lock into position. Swirl ribbons stop moving. The pint interior changes from fillable product into firm, frozen ice cream. Fast hardening limits the growth of large ice crystals and preserves the smooth frozen structure created in the continuous freezer. A filled Tillamook ice cream carton enters a blast hardening tunnel while the product inside is still soft enough to carry swirls, chips, cookie pieces, or fruit ribbons in suspended layers. Cold air rushes around the carton from multiple directions. The ice cream has already been partially frozen before filling, but it has not reached its final firmness. Inside the hardening tunnel, the remaining liquid water freezes rapidly. The smooth dairy base stiffens, added pieces lock into position, and any ribboned sauce stops flowing through the container. The carton moves through the tunnel on a belt or spiral conveyor. The residence time is controlled so the center of the package freezes deeply without damaging the paperboard carton. Rapid hardening keeps ice crystals small, preserving a dense, creamy texture after the carton leaves the factory freezer. Before a Tillamook carton can reach this stage, the ice cream must be built from separate liquid, flavor, inclusion, and packaging streams. The dairy base begins in stainless steel blending tanks. Milk and cream are pumped in through metered lines. The cream provides the fat structure that gives the frozen product its rich body. Sugar enters as a liquid syrup or measured dry ingredient. Milk solids, stabilizers, emulsifiers, and flavor-based ingredients are added according to the variety being produced. For a vanilla-style base, the mixture remains pale, while vanilla flavor disperses through it. For chocolate ice cream, cocoa ingredients enter through controlled powder feeders or slurry lines. Agitation pulls the cocoa into the liquid until the blend changes into a smooth, uniform brown mixture without visible dry streaks. The tank agitator turns steadily rather than violently. It must distribute ingredients completely while avoiding uncontrolled foaming. Sugar dissolves, powders hydrate, fat disperses through the water phase. Sensors track temperature and tank volume as the liquid blend reaches the correct composition. The mixed base is pumped into pasteurization equipment. It passes through narrow channels inside a plate heat exchanger. Heated fluid flows on the opposite side of the plates, transferring heat into the ice cream mix quickly and evenly. The liquid reaches its programmed treatment temperature while remaining enclosed in the processing system. Immediately after heating, the warm mixture enters a homogenizer. The liquid is forced through extremely small passages under high pressure. Large fat droplets break into much smaller droplets and spread more evenly throughout the mix. This mechanical reduction changes the behavior of the final ice cream. Instead of fat gathering in irregular patches, the base develops a smooth, consistent structure. The homogenized liquid leaves the machine with its dairy fat distributed finely through the sugar and water system. The hot base then travels through a cooling section of the heat exchanger. Chilled fluid removes heat through the stainless steel plates. The ice cream mix drops rapidly to a refrigerated temperature, still liquid but noticeably thicker than before pasteurization. The cooled mix enters aging tanks. These tanks remain refrigerated and contain slow-turning agitators. During aging, fat begins forming a more stable structure, while stabilizers finish absorbing water. The base becomes thicker and better prepared for freezing and aeration. The aging stage is quiet compared with the later machinery. The liquid moves slowly in the chilled tank, maintaining uniform temperature and consistency. When the required holding period is complete, pumps draw the aged mix toward the flavor and freezing line. Some Tillamook varieties receive liquid flavor adjustments after aging. Vanilla, coffee, caramelized flavor bases, strawberry preparations, chocolate components, or other recipe streams are pumped into the moving mix. Inline mixers blend them evenly before freezing. Varieties containing sauces require a separate swirl line. A caramel, fudge, berry, peanut butter, or cookie-based ribbon is made in jacketed kettles or blending vessels. Sugar syrups, fats, cocoa, fruit preparations, dairy ingredients, and flavor components are mixed under controlled heat. The swirl cannot be watery. It must remain thick enough to form visible ribbons inside the frozen base. Once blended, it is cooled to a pumping temperature that allows smooth flow through hoses and injectors without melting the semi-frozen ice cream later. Chunk ingredients follow another route. Cookie. Pieces may begin as baked sheets or formed dough pieces that are cooled and broken into controlled sizes. Chocolate chunks can be molded, cooled, and screened. Brownie pieces can be baked, cooled, cut, and chilled before feeding. Each inclusion must meet a size range. Pieces that are too small disappear into crumbs. Pieces that are too large can obstruct feeders or produce irregular filling. Screens remove fine material and oversized clusters before accepted chunks enter refrigerated holding hoppers. The aged flavored base is now pumped into a continuous freezer. Inside the freezer barrel, the liquid contacts an extremely cold inner wall. A rotating dasher fitted with scraper blades continually removes the thin frozen layer forming against that wall and folds it back into the product. As freezing continues, the liquid becomes thick and semi-solid. Small ice crystals form rapidly instead of growing slowly into coarse pieces. Controlled air incorporation gives the ice cream enough softness and structure for filling while maintaining a dense, finished body. The ice cream does not leave the continuous freezer as a solid block. It exits as a heavy, cold ribbon that can still be pumped and deposited. It is firm enough to support additions, but fluid enough to settle into cartons without leaving large empty spaces. For flavors without chunks or ribbons, the semi-frozen base can travel directly toward the filler. For more complex varieties, the product first enters an ingredient integration system. Chilled chunks descend from hoppers through rotating feeders. The feeder meters them into the flowing ice cream at a steady rate. The product stream catches and surrounds each piece. Gentle movement is essential because aggressive mixing could crush cookies, smear brownies, or fracture chocolate pieces into fine fragments. The swirl is injected after or near the inclusion stage. Pumps deliver thick sauce through small nozzles into the semi-frozen base. The system does not blend it completely. It lays the sauce through the product as broad folds, narrow ribbons, or repeated streaks so that the pattern remains visible inside the finished carton. The combined ice cream stream now approaches packaging. Empty Tillamook cartons arrive nested or stacked in magazines. Mechanical separators release them individually and position them upright in holders. The paperboard containers have an inner barrier layer that resists moisture and frozen product contact. The carton carriers move beneath filling heads in exact intervals. The nozzle aligns with an open carton and deposits a measured amount of product. Thick ice cream folds downward into the package. Chunks remain distributed through the filling stream, while sauce ribbons bend and layer as the carton fills. The filling head stops at the programmed volume. The upper surface may show ridges created by the final movement of the semi-frozen stream. A leveling action can settle the top enough for closure without blending the swirl pattern away. Lids travel from a separate magazine. Suction pickers or transfer arms remove one lid at a time and place it onto the filled carton. Pressure closes it against the upper rim. The package now contains a soft frozen product protected for the hardening stage. A coding system marks the carton or lid with production data, while the package remains on the conveyor. Inkjet print heads deposit small characters rapidly as each carton passes. Vision equipment can verify that the mark is present and readable. The closed cartons enter the blast hardening freezer. Very cold air moves across the top, sides, and base of every package. Cartons may travel in long rows or rise through a spiral system that provides extended freezing time within a compact footprint. Inside each carton, the ice cream continues changing. The semi-frozen dairy matrix becomes rigid. Chocolate pieces, cookie chunks, fruit fragments, and sauce streaks are locked into their final arrangement. The exterior carton remains square as the product solidifies against its walls. The lid is pressed onto a filled Häagen-Dazs cup, while the ice cream beneath it is still soft enough to form a gentle spiral at the surface. The closed cup immediately enters a hardening freezer. Inside, extremely cold air circulates around the sides, base, and lid. The ice cream has already been partially frozen, but its structure is not yet locked. As the cup travels through the freezing system, more water turns into fine ice crystals. The dairy matrix stiffens, and the smooth spiral becomes fixed inside the package. This final freezing stage is only possible because the liquid base has already been built, heated, homogenized, cooled, aged, flavored, and partially frozen through a separate chain of equipment. For a vanilla-style production run, the formula begins with cream, skim milk or concentrated skim milk, sugar, egg yolk, and vanilla extract. These ingredients enter stainless steel blending vessels through measured pipes and feeders. Cream flows into the tank as a thick pale liquid. Milk follows through another line. Sugar enters in a controlled quantity and begins dissolving as the agitator turns. Egg yolk is introduced as a smooth liquid ingredient, dispersing through the dairy base and contributing to the rich custard-like structure. Vanilla extract is metered into the moving blend. The agitator does not violently whip the liquid. It circulates the mixture in broad, steady currents, distributing sugar, dairy fat, milk solids, egg yolk, and vanilla evenly through the tank. Other flavors begin with the same basic liquid handling system, then branch through different ingredient additions. Cocoa can be dispersed into the dairy blend for chocolate ice cream. Coffee concentrate can be pumped into the mix for a coffee variety. Fruit preparations can be processed separately before entering a fruit-based production stream. Once the blend is uniform, pumps move it toward pasteurization. The liquid enters a plate heat exchanger made from a stack of thin, stainless steel plates. The ice cream mix flows through narrow channels on one side of the plates, while a heating medium moves through neighboring channels. Heat passes rapidly through the metal. The dairy mixture warms evenly while remaining enclosed. It does not sit in an open kettle. It travels continuously through a controlled heating section, with temperature sensors monitoring the liquid as it reaches the required processing condition. The warm mix then enters a homogenizer. Inside this machine, high-pressure pumps force the liquid through extremely narrow valve openings. The larger fat droplets in the cream are broken down into much smaller droplets and distributed more evenly through the mix. The change is microscopic, but the effect determines the finished texture. The homogenized liquid no longer carries larger uneven fat globules. It becomes a smoother, more stable base, capable of freezing into a dense, consistent ice cream body. Directly after homogenization, the hot mixture enters a cooling section. In another plate heat exchanger, chilled fluid runs close to the product stream on the opposite side of the stainless steel plates. Heat leaves the mixture quickly, dropping it to a refrigerated temperature. The cold liquid is pumped into aging tanks. These vessels are insulated and chilled, with slow-moving agitators keeping the mix uniform. During aging, The fat structure firms slightly and the liquid becomes thicker. Egg yolk and milk solids remain evenly dispersed while the base develops the body needed for freezing. The aged mixture is still pourable, but it moves more heavily than the original blend. It is cold, smooth, and ready to form small ice crystals inside the continuous freezer. Before freezing, the production line can add final liquid flavor components. Vanilla extract already distributed in the base may be balanced through the programmed flavor stream. Chocolate, coffee, caramel, or fruit varieties receive their own measured additions through closed pipes and inline mixers. For flavors containing ribbons, the sauce is made separately. A caramel ribbon begins in a heated blending vessel, where sugar-based ingredients, dairy components, and fat are mixed until smooth. A chocolate sauce uses cocoa ingredients blended into a flowing syrup system. A fruit ribbon begins as a prepared fruit mixture, adjusted to a thick, pumpable texture. The ribbon mixture is cooled before it meets ice cream. It must move cleanly through pumps and nozzles, but it cannot be so warm that it melts the semi-frozen base. Its thickness is controlled so it remains as visible folds rather than disappearing into the ice cream. Solid inclusions follow another separate path when the variety contains pieces. Chocolate chips or chocolate flakes are formed, cooled, and screened to the required size. Cookie pieces are baked or formed, cooled, broken, and classified. Fruit pieces are prepared into small, cold, free-flowing portions. The inclusion pieces pass through sizing equipment. Fine crumbs fall away, oversized clusters are separated. Accepted pieces collect in chilled holding hoppers above the inclusion feeder, ready to enter the frozen product without warming it. The aged ice cream base now enters the continuous freezer. This machine contains a refrigerated cylindrical barrel. The liquid mix flows through the center while the inner barrel wall becomes intensely cold. A rotating dasher turns inside the barrel. Scraper blades run close to the metal surface, shaving away the thin frozen layer that forms against it. Instead of allowing a thick sheet of ice to build on the wall, the blades continuously break the frozen layer into tiny crystals and fold them through the moving mixture. The liquid thickens quickly. At the freezer inlet, it flows like chilled cream. Farther along the barrel, it becomes heavier and slower. By the outlet, it emerges as semi-frozen ice cream, smooth, dense, and firm enough to hold shape, but still soft enough to pump and fill. A controlled amount of air can be incorporated during freezing. The air enters as very small cells dispersed through the frozen mix. The system keeps the structure dense rather than excessively expanded, allowing the finished cup to hold a rich, compact, frozen body. For a plain vanilla variety, the semi-frozen product can travel directly from the freezer toward the filling machine. For a variety with pieces, it enters the inclusion stage first. A rotating feeder draws chilled chocolate, cookie, or fruit pieces from the hopper. It releases them into the thick ice cream stream at a measured rate. The pieces are folded gently into the product. They do not need heavy mixing. The moving ice cream captures them and carries them forward. For a ribboned variety, a swirl injector introduces caramel, chocolate, fruit, or another prepared sauce after the base has thickened. Narrow nozzles feed the sauce into the stream in controlled bands. The line avoids blending it completely, preserving streaks that remain separate within the frozen body. The filled product stream approaches the packaging area through insulated pipework. Empty cups are fed from stacked magazines. Mechanical separators release one cup at a time and position it upright inside carriers on an indexing conveyor or rotating filling table. The cups are made from coated paperboard or another frozen product package structure. Their inner surface resists moisture from the ice cream, while the outer surface carries the printed design. Each cup reaches the filler with its open top aligned directly beneath the nozzle. The filling head lowers into position. Semi-frozen Häagen-Dazs flows downward into the cup in a thick ribbon. plain ice cream folds over itself in a smooth spiral. Chunk-containing varieties deliver pieces suspended through the stream. Ribboned varieties create visible curved layers as sauce and ice cream settle together. The filler stops at the precise target amount. The upper surface remains below the rim so the lid can seat cleanly. A small finishing motion may shape or level the top without pressing the ice cream flat. Lids arrive from another magazine. A pick-and-place mechanism removes one lid at a time and places it over each filled cup. Pressure seats the lid around the rim. In sealed formats, an inner membrane or sealing component can be applied before the outer lid is fitted. A coding head marks the package with production information. The code is applied to the lid, cup base, or side panel while the container remains in motion. Sensors inspect the lid position and confirm that a closed cup continues toward hardening. The freshly lidded cups are still soft inside. They transfer immediately into the hardening freezer. The packages may travel on a long belt or through a spiral conveyor that carries rows of cups upward and downward inside a compact refrigerated chamber. Paper cups move through the Reese's line as tiny, empty molds before any peanut butter appears. They are thin, fluted, and shaped to give the candy its ridged edge. A feeder separates the cups one by one from a stacked magazine. Each cup drops into a pocket on a moving tray or conveyor. The pockets hold the cups open and steady so chocolate can be deposited accurately. The first layer is the chocolate base. Milk chocolate is held in a temperature-controlled tank. It has already been mixed, refined, conched, and tempered before reaching the depositor. The chocolate must be fluid enough to flow into every crease of the paper cup, but stable enough to set with a firm shell after cooling. Tempering is critical. The chocolate is cooled and gently reheated through a precise temperature path so the cocoa butter forms stable crystals. This allows the shell to contract slightly as it sets, hold its shape, and release cleanly from equipment without becoming soft or dull. A depositor lowers over the empty paper cups. Nozzles release a measured amount of chocolate into each one. The chocolate lands in the center and spreads outward across the bottom. It flows into the fluted edges, forming the first part of the cup shell. The conveyor then passes through a vibrating section. The vibration settles the chocolate and removes trapped air bubble. The surface levels out. The chocolate creeps evenly into the ridges of the paper liner. Some lines use spinning or shaking to move chocolate up the cup wall. The goal is not to fill the cup with chocolate at this stage. The goal is to create a bottom layer and side coating that can hold the peanut butter center later. The cups enter a cooling tunnel. Chilled air passes over and under the moving trays. The chocolate firms from the outside inward. It becomes strong enough to support the next deposit, but not so cold that the later chocolate layers fail to bond to it. While the chocolate shells are cooling, the peanut butter filling is prepared separately. Roasted peanuts enter grinding equipment. They are crushed into a thick paste as rotating plates or rollers break the nuts down. Oil naturally present in the peanuts releases during grinding, turning the dry pieces into a smooth, heavy peanut butter mass. The paste is not yet the finished filling. Reese's filling has a distinct texture, dense, slightly grainy, sweet, and firm enough to hold its shape inside the chocolate cup. To create that structure, the peanut paste is blended with sugar, salt, and other formula ingredients in a heavy mixer. Sugar enters as a fine, dry ingredient. It does not disappear completely into the peanut paste like sugar in a liquid syrup. Instead, it becomes part of the filling texture. The mixer folds the sugar through the peanut mass until the mixture becomes uniform. Salt is added in a controlled amount. It spreads through the paste as the mixer turns. The filling becomes more defined in flavor and slightly drier in body. The mixer blades press, lift, and fold the material repeatedly, creating a cohesive filling that can be shaped and deposited. Fat content and temperature control the flow of the filling. If the mixture is too stiff, it will not deposit cleanly. If it is too soft, it can spread into the chocolate shell and rise unevenly. The filling must sit in the center as a compact disc. The prepared peanut butter filling moves into a hopper above a forming or depositing machine. In some systems, the filling is extruded as a thick rope and sliced into small portions. In others, a piston depositor pushes measured amounts directly into the chocolate-lined cup. The cooled chocolate shells arrive under the filling depositor. Each nozzle releases a precise portion of peanut butter into the center of the cup. The deposit lands as a round mound or disc. It does not reach the outer edge completely. completely. A narrow ring of space remains around it so the final chocolate layer can seal the filling inside. The filling surface may be lightly flattened by the depositing motion or by a gentle leveling mechanism. The goal is a centered, even peanut butter mass with enough clearance for chocolate to cover the top and side. Now the cup has three visible parts: the fluted paper liner, the set chocolate base and wall, and the peanut butter center sitting inside it. The candy is still open at the top. The trays advance to the second chocolate depositor. Tempered milk chocolate is delivered again through heated lines. The temperature is maintained carefully so the chocolate remains fluid without losing its temper. A measured amount of chocolate drops onto the peanut butter center and surrounding edge. It spreads outward, flows over the filling, and joins the chocolate side wall. This top layer completes the sealed cup. The deposit must be balanced. Too little chocolate leaves exposed filling or a weak seam. Too much makes the top too thick and changes the shape. The depositor controls the amount for every cup, repeating the same short pulse across rows of moving mold. The cups pass through vibration again. The top chocolate settles into a smooth surface and connects with the lower shell. Air pockets rise and break. The surface becomes flatter, with a slight central softness before cooling locks it in place. The filled cups now enter the main cooling tunnel. Air temperature, airflow, and belt speed are controlled so the chocolate sets evenly. The bottom, side ridges, and top layer all crystallize into one continuous shell around the peanut butter filling. Cooling must not be too aggressive. Chocolate cooled too quickly can crack or lose surface quality. Cooling too slowly leaves the cup soft and vulnerable to smearing during wrapping. The tunnel sets the chocolate while keeping the peanut butter center stable inside. As the cups leave the cooler, the chocolate is firm. The paper liners still hold the ridge shape. The top surface is set and the peanut butter center is completely enclosed. Inspection begins before wrapping. Cameras check cup shape, top surface, missing chocolate, exposed filling, damaged paper liners, and broken edges. Weight systems can verify that the chocolate and filling deposits are within range. Metal detectors scan the finished candy flow. Rejected pieces are removed automatically. Accepted cups continue into alignment equipment. The pieces must be oriented and spaced for the wrapping line. Many Reese's cups are packed in pairs. The conveyor brings individual cups into lanes, then timing belts group two cups together. The paired cups are positioned flat, side by side, with their paper liners facing downward and their chocolate tops protected from direct scraping. Printed wrapper film unwinds from a roll. The film passes through tension rollers and registration sensors. The sensors read printed marks, so the design lines up correctly with each pair of cups. The grouped cups enter a flow wrapper. The film folds around them, forming a tube. A longitudinal seal closes along the underside or back of the wrapper. Heated sealing wheels press the film layers together while the product continues moving. Cross-seal jaws close at the front and back of each pack. The jaws press, seal, and cut, separating one wrapped pair from the next. The wrapper forms a tight but protective package around the cups without crushing the ridges or deforming the chocolate. Single cup formats use the same principle with different spacing and film length. Miniature cups follow a smaller depositing and wrapping route, often with foil or twist-style wrapping equipment. The main sequence remains the same: chocolate shell, peanut filling, chocolate cover, cooling, inspection, and wrapping. Wrapped packs pass through another inspection stage. Vision systems check wrapper alignment, seal integrity, code placement, and damaged film. Check weighers verify that each pack contains the proper amount of product. Packs outside tolerance are diverted away from the accepted flow. A coding printer applies production information to each wrapper or retail pack. The mark is small and sharp, printed while the pack moves at high speed. It identifies the batch and line timing. Individual packs may continue directly to case packing, or they may move into multi-pack assembly. For multi-packs, several wrapped Reese's units are collated into a controlled arrangement. Mechanical fingers or belt group them into rows before a secondary wrapper or carton encloses them. A long caramel-covered slab moves forward as one continuous Mars bar before it is divided into individual pieces. At this point, the product is not yet coated in chocolate. It is a layered strip, soft nougat underneath, caramel spread across the top, both moving together on a wide conveyor. The slab is firm enough to cut, but still flexible enough to show the difference between its two textures. The nougat is lighter and aerated. The caramel is darker, glossier, and heavier. The nougat layer begins in a mixing system built for dense confectionery stationary foam, sugar syrup, glucose syrup, and water are cooked in heated vessels until the mixture reaches the correct solids level. As moisture evaporates, the syrup thickens and becomes more elastic. Temperature control is critical because the finished nougat must be soft, chewy, and stable after cooling. A whipping phase is prepared separately. Egg albumin or another aerating ingredient is hydrated and beaten into a foam structure. The hot syrup is introduced into this aerated base while the mixer turns continuously. The syrup streams into the foam and strengthens it. The mixture expands, becoming lighter in color and thicker in body. Additional ingredients are blended into the nougat mass. Fat, milk components, cocoa or malted flavor elements, and other formula ingredients are mixed until the texture becomes smooth and uniform. The nougat must hold tiny air cells without collapsing. It also has to remain soft enough to bite through after the bar is finished. The mixer discharges the nougat as a warm, thick mass. It does not pour like liquid. It moves slowly, stretching and folding as it leaves the bowl or continuous mixer. The nougat is transferred to a forming line where rollers and spreading equipment turn it into a uniform sheet. The sheet passes between calibrated rollers. Each roller pair controls thickness and width. Side guides keep the nougat from spreading too far. The surface becomes level as the sheet advances, creating the base layer for the Mars bar. If the layer is too thick, the bar becomes heavy and unbalanced. If it is too thin, it cannot support the caramel properly. The formed nougat enters a cooling tunnel. Cool air firms the structure so it can receive caramel without deforming. The nougat is not hardened completely. It remains soft and elastic, but its surface becomes strong enough for the next layer. Caramel is prepared on another line. Sugar, glucose syrup, milk ingredients, fat, and water enter heated cooking vessels. Agitators keep the mixture moving while heat drives off moisture. The caramel darkens gradually as the sugars cook and the milk components develop flavor and color. The caramel must reach a precise flow texture. It needs enough body to sit on the nougat as a clean layer, but enough softness to stretch during eating. A caramel that is too fluid would run off the slab. A caramel that is too firm would cut poorly and separate from the nougat. After cooking, the caramel passes through cooling or tempering equipment that brings it to a depositing temperature. It remains pumpable, glossy, and thick. Heated pipes carry it toward the layering station above the nougat sheet. The nougat sheet travels under a caramel depositor. A wide slot nozzle or series of nozzles lays caramel across the surface. The caramel spreads into a smooth band from edge to edge. Leveling rollers or controlled blades adjust the thickness so the layer remains even across the full width of the slab. The two layers now move together. The warm caramel bonds to the cooled nougat surface without melting it completely. The slab passes through another cooling section, so the caramel gains enough structure for cutting. The surface becomes less fluid, but keeps its glossy appearance. The layered slab approaches the slitting station. Long circular knives rotate above and below the conveyor. They cut the wide sheet lengthwise into narrow ropes. Each rope has the same cross-section, nougat below, caramel above. The cut edges reveal the pale interior and dark top layer. The ropes continue forward with small spaces between them. A cross-cutting machine then divides them into individual bar lengths. A guillotine blade or rotating cutter moves in rhythm with the conveyor. Each cut must pass cleanly through caramel and nougat without dragging the caramel down the sides or compressing the nougat. The freshly cut bars now have exposed sides. They are recognizable in shape, but they are not finished Mars bars. They must be completely covered in milk chocolate. Before coating, the cut centers may pass through a short conditioning zone. This stabilizes surface temperature and reduces stickiness. The bars must enter the enrober with a controlled surface condition. If the caramel is too warm, it can smear. If the center is too cold, chocolate may set too quickly and coat unevenly. Milk chocolate is prepared in a separate processing system. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are mixed into a thick chocolate mass. The mixture is refined through rollers that reduce particle size. Refining changes the texture from coarse to smooth. The refined chocolate moves into conching equipment. Heavy mixing arms work the chocolate for a controlled period. The fat coats the dry particles more evenly, and the chocolate becomes smoother and more fluid. Its flow behavior is adjusted so it can cover the bar cleanly in the enrober. Before coating, the chocolate is tempered. It is cooled and gently reheated through a precise temperature curve. This creates stable cocoa butter crystals. Proper tempering allows the chocolate shell to set firm, smooth, and glossy after cooling. The Mars centers enter the enrober on a wire mesh belt. The belt carries them beneath a curtain of tempered milk chocolate. The chocolate falls over the caramel top, runs down the sides, and covers the nougat edges. At the same time, chocolate is applied from below through the mesh belt, so the underside is coated. Excess chocolate drains back through the belt and returns to the circulation system. The bars pass beneath controlled air blowers. These remove extra chocolate from the top and sides and help control the shell thickness. The airflow must be strong enough to smooth the coating, but not so strong that it exposes caramel or nougat. A vibrating section helps the chocolate settle. Tiny trapped air bubbles rise out of the coating. The chocolate surface becomes smoother as the bar continues forward. The coating begins to define the final shape, rounding the corners and sealing the layered center. The enrobed bars enter a cooling tunnel. Chilled air flows around the moving belt. The chocolate begins to crystallize and firm. The liquid surface changes into a stable shell. The nougat and caramel remain soft inside, while the outside becomes strong enough for wrapping. Cooling must be gradual and controlled. If the chocolate sets too fast, it can crack or lose surface quality. If it sets too slowly, the bars can smear on guides and belts. The tunnel balances air temperature, humidity, and belt speed until the coating is fully set. At the exit, the bars pass through inspection. Cameras check shape, coating coverage, surface marks, broken corners, exposed centers, and incorrect size. Metal detection scans the product stream. Bars that do not meet the programmed limits are rejected automatically. Accepted bars enter the wrapping section. Timing belts space them evenly and align them lengthwise. Printed film unwinds from a roll and passes through tension rollers. Registration sensors read marks on the film so the graphics align with each bar. The bar enters a flow wrapper. The film folds around it, forming a tube. A longitudinal seal closes along the underside. Heated sealing wheels press the film together while the bar continues moving forward. Cross-seal jaws close the front and back ends, sealing and cutting one pack from the next. Wrapped bars travel through check weighers. A missing, broken, or incorrect bar produces a weight outside the allowed range and is rejected. Vision systems check wrapper position, seal quality, code presence, and print alignment. A tall wafer sheet reaches the cutting section as a layered block, and sharp blades divide it into long, narrow Kit Kat fingers. The block already contains several crisp wafer layers bonded together with cream. Before cutting, it is wide and flat, like a large rectangular board made from thin biscuit sheets. The blades slice through the stacked structure cleanly, separating it into uniform strips. Each strip shows the internal pattern: wafer, cream, wafer, cream, wafer. The cut must be exact. If the blade pressure is too high, the fragile wafer cracks. If the blade is dull, the cream layer drags and smears across the edges. The cutting system holds the wafer slab steady while rotary knives or straight blades divide it into precise finger widths. After the first cuts, cross-cutting blades divide the long strips into bar lengths. The individual centers are still not coated in chocolate. They are light, crisp wafer pieces with visible layers and exposed edges. These centers move toward conditioning before enrobing. To reach this stage, the wafer begins as a thin batter. Flour, water, sugar, fat, salt, leavening ingredients, and other minor components are measured into a mixing system. The batter is much thinner than cookie dough. It must spread quickly across hot baking plates and form a delicate sheet with a fine, crisp texture. Dry ingredients pass through sifters before mixing. The screens remove lumps and oversized particles. This prevents blocked batter pumps and uneven wafer texture. The powders enter a blending tank while water and liquid ingredients flow in through metered lines. Agitators rotate inside the batter tank. The flour hydrates and disperses. The mixture becomes smooth, pale, and pourable. Air content and viscosity are controlled because the batter must form a thin sheet without tearing or sticking to the wafer plates. The finished batter moves to a wafer oven. This oven is built from many hinged metal baking plates that travel in a continuous chain. Each plate pair opens, receives a measured deposit of batter, closes, bakes the sheet, opens again, and releases the wafer. A depositor spreads a precise amount of batter onto the hot plate. The upper plate closes, pressing the batter into an extremely thin layer. Heat reaches the batter from both sides. Water inside the batter flashes into steam, helping create the wafer's porous structure. Inside the closed plates, the batter sets quickly. Starch gelatinizes, proteins firm, moisture evaporates. Small bubbles leave a light network inside the sheet. The wafer becomes dry, crisp, and patterned by the plate surface. When the baking plates open, a large wafer sheet releases from the metal. It is thin, brittle, and warm. Transfer arms, or belts, carry it away from the oven. The sheet must be handled gently because any bending can crack it before layering. The baked wafers pass through cooling conveyors. Warm air and then cooler air remove heat evenly. Cooling stabilizes the crisp structure and prevents steam from softening the sheets while they are stacked. The wafers become firm enough for cream application. Wafer cream is prepared in a separate mixing system. Sugar, fat, cocoa or milk components, flavoring, and finely ground wafer material can be blended into a smooth filling. The texture must be spreadable, not runny. It needs to hold the wafer layers together without soaking into them and destroying the crispness. The cream mixer works the fat and powders into a uniform paste. It becomes smooth enough to pass through rollers and spreaders. Temperature control keeps the cream soft for application, but stable enough to remain in an even layer. The cooled wafer sheets reach the layering station. One wafer sheet lands on a conveyor as the bottom layer. A spreading head applies a thin film of cream across the entire surface. The layer must be even from edge to edge. Too much filling makes the stack heavy and soft. Too little creates weak bonding between wafers. A second wafer sheet is placed on top of the cream. Another layer of cream is spread across it. More wafer sheets are added in sequence until the stack reaches the required height. The stacking machine aligns the sheets precisely so the edges remain square. Each wafer layer contributes crispness. Each cream layer bonds the structure and carries flavor. The stack must stay dry enough to snap, but strong enough to pass through cutting, coating, wrapping, and packing. Once assembled, the large wafer stack enters a cooling or setting tunnel. The cream firms slightly, locking the sheets together. The block becomes stable enough to cut without sliding apart. The top and bottom surfaces remain flat, and the internal layers hold their position. The set wafer block then moves to trimming. Uneven outer edges are removed, so the slab has straight sides. Trimmed fragments can be collected and processed for use in cream or other controlled ingredient streams. The squared slab continues to the finger cutting section. This is where the bar begins to take its familiar shape. Long knives cut the slab lengthwise. The separated strips move forward and are cross-cut into shorter centers. Depending on the product format, several fingers may remain joined or be later arranged as a multi-finger bar. After cutting, the wafer centers pass through separation equipment. Small gaps open between the pieces so chocolate can cover every exposed surface. Conveyors and timing belts align them in rows, keeping them straight before the enrober. Chocolate preparation runs separately from the wafer line. Cocoa ingredients, sugar, milk powder, cocoa butter, and fats are combined into a chocolate mass. The mixture is refined through rollers to reduce particle size and create a smooth mouthfeel. The refined chocolate moves into conching equipment. Heavy mixing arms work the chocolate until it becomes fluid, uniform, and smooth. The fat coats the cocoa, sugar, and milk particles. The chocolate develops the correct flow for coating fragile wafer centers. Before enrobing, the chocolate is tempered. It is cooled and reheated through a controlled temperature curve. Stable cocoa butter crystals form in the chocolate. This allows the coating to set with a firm surface and clean snap after cooling. The wafer centers enter the enrober on a wire mesh belt. A curtain of tempered chocolate falls from above. Each wafer piece passes through it, and chocolate flows over the top, down the sides, and across the exposed layered edges. Chocolate also coats the underside through the mesh belt. Excess chocolate drains away and returns to the circulation system. The coating must seal the wafer center without making the bar too heavy. A Kit Kat relies on a balance between crisp wafer and chocolate shell. Air blowers remove extra chocolate from the top and sides. The airflow controls thickness and smooths the coating. If too much chocolate remains, the bar loses its sharp wafer profile. If too little remains, the wafer can show through or the shell may be weak. The bars may pass over a vibrating section. This helps release trapped air bubbles and smooth the chocolate surface. The coating settles into a continuous shell around the wafer fingers. Some Kit Kat formats include molded details or a shaped chocolate top. In molded processes, chocolate is deposited into molds first, wafer centers are placed inside, and more chocolate seals the bottom. In enrobing processes, the coating forms around the moving center. Both routes are designed to surround the crisp wafer stack with with chocolate while preserving the internal layers. The coated bars enter a cooling tunnel. Chilled air flows around them while the belt moves steadily forward. The chocolate begins to crystallize and harden. The liquid shine becomes a firm surface. The wafer inside remains dry because the shell forms a protective barrier. A finished Dunkin' Donut crosses beneath a curtain of glaze, and its warm surface changes from matte gold to glossy white in a single pass. The donut has already been mixed, proofed, fried, and cooled to the exact point where glaze will cling without sliding away. It rides on an open mesh conveyor. Below the belt, excess glaze drains through and returns to a heated circulation tank. Above it, the glaze falls in a smooth sheet, coating the top, sides, and inner ring. The glaze begins as sugar, water, flavoring, and texture control ingredients blended inside a heated tank. Agitators keep the liquid moving so it stays uniform. The glaze must be thick enough to coat the donut, but fluid enough to flow evenly across the surface. If it is too thin, it leaves bare spots. If it is too thick, it builds heavy ridges. After glazing, the donut moves into a setting zone. Conditioned air passes over the surface. Moisture begins leaving the coating. The glaze changes from wet and glassy to a soft, set shell that still looks shiny but no longer runs. Decorated donuts follow another route after frying. A chocolate-frosted donut passes beneath a coating head that deposits melted chocolate icing across the top. The donut may be lifted slightly or guided under a roller, so the icing spreads into a smooth cap. Excess coating is controlled by flow rate, temperature, and belt speed. Sprinkled donuts are coated while the icing is still tacky. A dispenser drops colored sugar pieces in a steady stream. The sprinkles strike the wet surface and remain embedded as the icing sets. Loose pieces fall through the belt and are separated from the finished flow. Filled donuts skip the center hole. They begin as round dough pieces that are fried whole. After cooling, they pass through an injection station. Thin filling nozzles enter from the side. A measured dose of jelly, cream, custard, or flavored filling is pumped into the interior. The filling expands the soft center without bursting the outer wall. Before any of these finishing stages can happen, the donut starts as dough. Flour enters the mixing area from storage bins or ingredient bags. It passes through a sifter that breaks up compacted lumps and removes oversized material. Sugar, salt, yeast, milk-based powders, leavening ingredients, and flavor components are measured in separate dosing systems. Liquid ingredients enter through metered lines. Water controls hydration. Egg ingredients add color and structure. Oil or shortening adds tenderness. The water temperature is adjusted because dough temperature affects yeast activity and proofing speed. The ingredients enter an industrial mixer. The mixer begins slowly, pulling flour into the liquid. Dry streaks disappear as the mass thickens. The dough moves from loose clumps to a single elastic body. The mixing arms stretch, fold, and compress it repeatedly. The dough must develop enough strength to trap gas during proofing, but it cannot become tough. A raised donut needs a soft bite, not a bread-like chew. Mixing time, dough temperature, hydration, and fat content are controlled so the dough sheets, cuts, and fries correctly. The finished dough leaves the mixer in heavy portions. It may pass through a divider that cuts it into manageable blocks. These blocks rest briefly so the gluten relaxes. Relaxed dough moves more smoothly through rollers and keeps its shape after cutting. The dough enters the sheeting line. Large rollers pull it into a thick band. Additional roller pairs reduce the thickness gradually. Each pass flattens the dough without tearing it. The surface becomes smooth and even. A light dusting system may apply flour to prevent sticking. Scrapers keep dough from wrapping around rollers. Side guides keep the sheet aligned as it travels forward. For ring donuts, a rotary cutter presses into the dough sheet. Circular cutting edges form the outer ring, while smaller cutters remove the center hole. The cutter repeats the pattern across the moving sheet, producing rows of pale, raw rings. The scrap dough between the rings is lifted away. It can be returned to the dough system in controlled amounts. The small centerpieces may be carried to a separate line for donut holes. For filled donuts, the cutter forms solid rounds instead of rings. For shaped seasonal donuts, patterned cutters create special outlines. The forming principle remains the same. A uniform dough sheet is cut into exact shapes before proofing. The cut dough pieces are delicate. They move onto proofing trays or belts and enter a warm, humid chamber. Inside the proofer, yeast becomes active. It consumes sugars and produces carbon dioxide. The gas collects inside the dough structure, expanding each piece. The rings rise slowly. Their surfaces remain soft because humidity prevents drying. The dough becomes lighter, taller, and more fragile. A properly proofed donut has enough gas inside to float and expand during frying without collapsing. From the proofer, the donuts transfer to the fryer. The transfer must be gentle. A rough drop would distort the ring or deflate the proofed structure. The fryer contains hot oil moving through a stainless steel channel. The dough pieces enter and begin floating almost immediately. Moisture at the surface flashes into steam. The outside sets into a thin crust while the inside expands. One side fries first. The surface turns golden as sugars and proteins brown. A turning mechanism flips the donut at the correct point. The second side enters the oil and browns to match the first. The ring shape becomes stable, with a soft interior and a tender crust. Oil temperature is held within a narrow range. If it is too low, the donuts absorb too much oil and become heavy. If it is too high, the outside darkens before the inside cooks. Crumb filters remove loose particles from the oil so burnt fragments do not stick to later donuts. The fried donuts leave the oil on a draining conveyor. Excess oil falls through the belt. The donuts are hot, soft, and fully cooked. They move through an initial cooling section so the crust firms before finishing. Plain glazed donuts reach the glaze curtain while still slightly warm. The warmth helps the glaze flow and bond. Frosted donuts cool further, so chocolate or icing sets cleanly on top. Filled donuts cool enough that injected cream or jelly remains stable inside. Different product lines branch from this point. A powdered donut moves through a dusting drum or sugar application chamber. Fine powdered sugar coats the surface as the donut tumbles gently or passes under a falling layer. Excess powder falls away through screens. A cinnamon sugar donut receives a dry coating, while the surface still has enough warmth and oil to hold the crystals. The donut tumbles through the mixture, picking up a sandy coating across its outer crust. A Boston cream-style donut is first injected with cream filling. Then the top surface passes under chocolate icing. The icing spreads into a smooth cap and sets as the donut cools. A jelly donut is filled from one side. The injection system controls the dose, so the filling reaches the center without leaking through the crust. After filling, the donut can be sugared, glazed, or left with a plain exterior depending on format. Finished donuts travel through inspection. Cameras can check shape, color, topping coverage, missing decoration, broken edges, and filling leaks. Check weighers can detect missing filling or incorrect product size. Donuts that do not match the programmed range are removed from the line. For retail packs, donuts are grouped by type and count. Conveyors guide them into lanes. Timing belts space them carefully because toppings can mark if they touch too hard. Mechanical pick-and-place systems, or soft transfer belts, place donuts into trays, cartons, or clamshell packs. A tray pack begins with a formed plastic or paperboard tray. Donuts are placed into individual pockets or arranged in rows. The tray protects icing, glaze, and toppings from direct contact with other products. Krispy Kreme production begins when proofed dough rings slide from the proofer and settle onto the surface of hot frying oil. The rings are pale, swollen, and full of tiny gas cells. They are not dense pieces of raw dough anymore. They have expanded in warm humidity until they are light enough to float. As soon as they enter the oil, the bottom surface begins setting into a golden crust. The fryer carries the rings forward in straight lanes. Oil surrounds the lower half of each donut, while steam pushes outward from the dough. The ring grows, slightly larger. The surface firms. The inside becomes soft, open, and airy. A turning mechanism flips each donut at the correct point. The pale top becomes the second fried side. Bubbles race around the outer edge and the center hole. The second surface browns to match the first, creating a light golden shell around a tender, yeast-raised crumb. The oil temperature must stay steady. If it drops too low, the donuts absorb too much oil and become heavy. If it rises too high, the crust darkens before the center cooks properly. Filters remove loose crumbs from the oil, so burnt particles do not cling to the next row. The fried rings leave the oil on a draining conveyor. Excess oil falls through the open belt. The donuts are still hot and delicate. Their crust is firm enough to handle, but the interior remains soft and springy. Before the fryer, the dough begins in a mixing system. Flour enters from storage or bags and passes through a sifter. The sifter breaks up compacted flour and removes oversized particles. Sugar, salt, yeast, milk-based powders, and other dry ingredients are weighed separately. Each addition is measured because small changes alter dough strength, fermentation, and final texture. Water enters through a temperature-controlled line. Liquid egg ingredients, shortening or oil, and flavor components are added according to the dough formula. The temperature of the water is adjusted to control the final dough temperature after mixing. The mixer starts slowly. Flour absorbs water. Dry ingredients disappear into the liquid phase. The mixture first becomes rough clumps, then gathers into a single dough mass. The mixing arms fold, stretch, and compress it repeatedly. A Krispy Kreme style yeast-raised dough needs enough elasticity to trap gas, but not so much strength that the donut becomes chewy. The mixer develops the dough until it can expand smoothly during proofing and still fry into a tender crumb. The finished dough leaves the mixer in a heavy mass. It may rest briefly to relax. This short rest makes the dough easier to sheet and cut without shrinking back. The dough moves through rollers that flatten it into an even sheet. The first rollers reduce the thick mass. Later rollers refine the thickness. The sheet becomes smooth, continuous, and uniform from edge to edge. A light flouring system prevents sticking to belts and rollers. Scrapers keep dough from wrapping around moving surfaces. Side guides hold the sheet in alignment as it approaches the cutter. The rotary cutter presses ring shapes into the moving sheet. One circular blade forms the outer edge. A smaller center blade removes the hole. Rows of raw rings separate from the dough web with every rotation. The unused dough between the rings is lifted away and can be returned in controlled amounts. The center pieces may be carried separately for small dough bites or removed from the ring line. The raw rings are much flatter than finished donuts. They enter the proofing stage, where their structure changes slowly. The proofer is warm and humid. Yeast becomes active and produces carbon dioxide inside the dough. The gas expands the internal network, making the rings taller and lighter. Humidity keeps the surface from drying. A dry skin would restrict expansion and create cracks during frying. The rings ride through the chamber on trays or belts, growing gradually until they reach the correct height and softness. A properly proofed ring is fragile. The transfer from proofer to fryer must be smooth. Sudden impact can collapse the internal gas cells or distort the center hole. The equipment releases the dough gently into the hot oil. After frying and draining, the donuts move toward the glaze section while still warm. The glaze is prepared in a heated tank. Sugar, water, and flavoring components blend into a smooth liquid. Agitation keeps it uniform. The temperature and solids level control how the glaze flows across the donut and how it sets afterward. The glaze circulates from the tank to a depositor above the conveyor. It falls as a continuous curtain. The hot donuts pass through the curtain, and the glaze covers the top surface, outer edge, inner edge, and part of the underside. Excess glaze drains through the mesh belt and returns to the tank. The warmth of the donut helps the glaze spread into a thin, even coating. The liquid fills tiny surface pores, then begins to set as the donut continues forward. The surface changes from wet, shine to a smooth, delicate sugar shell. The glazed donuts enter a cooling and setting section. Air moves across the rows. Moisture leaves the glaze. The coating becomes less sticky while remaining glossy. The donut inside stays soft because the setting stage is focused on the surface, not on drying the crumb. Other Krispy Kreme donut varieties branch from the plain ring line or from separate dough shapes. For chocolate-iced donuts, fried rings cool slightly before passing under a chocolate icing applicator. The icing is held at a controlled temperature so it flows over the top but does not run off completely. The donut touches or passes beneath the coating stream, creating a smooth cap. For sprinkled donuts, decorations are applied while the icing is still tacky. A dispenser releases colored sugar pieces across the top. Loose sprinkles fall between the products and are separated from the finished stream. For filled donuts, the dough is cut as a solid round instead of a ring. The rounds proof and fry in the same general way, but they leave the fryer as closed pillows of soft dough. After cooling, they enter an injection station. Filling needles enter the side of each donut. A measured amount of cream, custard, jelly, or flavored filling is pumped into the center. The filling spreads through the soft interior without breaking the outer crust. The nozzles withdraw, leaving a small entry point. Filled donuts may then receive glaze, powdered sugar, icing, or stripes. A powdered donut tumbles gently through fine sugar or passes through a dusting chamber. A striped donut passes beneath narrow nozzles that apply thin lines of icing across the surface. Finished donuts continue into inspection. Cameras check shape, color, glaze coverage, missing decoration, cracked icing, exposed filling, or distorted rings. Weight checks can detect missing filling or incorrect size. Any donut outside the set limits is removed. The accepted donuts are separated by type and count. Conveyor lanes keep them aligned. Timing belts create gaps so glazed or iced surfaces do not rub together. Handling must be gentle because the sugar shell can mark and the crumb can compress. For boxed dozens, flat paperboard blanks are opened into boxes. Donuts are transferred into the box in a grid pattern. Plain glazed rings may be arranged closely because their coating is set. Iced or decorated donuts require more careful placement to avoid contact damage. Mechanical guides position each donut inside the box. The lid folds over the top. The box holds the donuts in place and protects the surface from direct pressure. For smaller retail packs, donuts can be placed into trays or clamshell containers. A tray keeps individual pieces separated. A clear lid or film cover protects the icing, glaze, and toppings while keeping the product visible through the package. For wrapped single-serve items, one donut enters a flow wrapper. Printed film folds around it. A back seal closes the film tube and end seal jaws close the package before cutting it free. The wrapper protects the donut surface and controls contact with air. Every pack passes through coding. Inkjet printers mark the box, tray label, wrapper, or case with production information. Vision equipment checks the code position and package closure. Packaged products move into secondary packing. boxes, trays, or wrapped units are grouped and loaded into corrugated cases. The case may be opened from a folded blank or formed around the product group. Flaps fold inward, adhesive is applied, and compression belts hold the case closed. Taco Bell production begins with seasoned beef being transformed from raw ground meat into a controlled, portionable filling. The beef enters a cooking system in measured batches. It is broken apart mechanically so it does not cook as large clumps. Heated kettles, steam-jacketed vessels, or continuous cookers bring the meat up evenly while mixing arms keep it moving. As the temperature rises, the red raw meat changes to a brown, crumbly texture. Fat and moisture release from the meat during cooking. The mixer folds the beef through its own juices, preventing dense sections from sticking to the hot surface. The goal is a fine, even crumble that can later spread smoothly inside tacos, burritos, and layered items. A seasoning blend is prepared separately. It contains dry spices, salt, dehydrated ingredients, thickening components, and flavor bases. The powder is kneaded into the cooked beef with a controlled amount of water or sauce base. Once added, the mixture darkens and becomes more cohesive. The beef does not remain dry. The seasoning liquid thickens around the particles, coating each crumble. The texture shifts from loose cooked meat to a sauced filling. This helps it portion cleanly and stay distributed inside the final product. The seasoned beef is mixed until its color, moisture, and particle size are uniform. It may then be pumped or transferred into pouch filling equipment. The hot filling enters food-grade pouches or trays in measured weights. Air is removed as much as possible before sealing. The sealed packs are heat-treated or chilled according to the production format, then packed into cases for controlled distribution. Another major component is the tortilla. Flour tortillas begin with wheat flour, water, fat, salt, leavening ingredients, and conditioners entering a mixing system. The mixer turns slowly at first, hydrating the flour. Then it develops the dough until it becomes smooth and elastic. The dough must stretch without tearing because burritos and wraps need flexible tortillas. The dough is divided into exact portions. Each portion becomes a dough ball. The balls rest briefly so the dough relaxes. Resting reduces spring back, allowing the tortilla to press into a flat circle. The dough balls enter a hot press. Upper and lower plates flatten each piece into a thin round disc. Heat partially sets the surface at the same time. The raw tortilla then passes through an oven where hot belts or heated plates finish cooking it. Steam forms inside the dough, creating small bubbles and light brown spots. The cooked tortillas pass through cooling conveyors. Air removes heat so the tortillas can stack without trapping moisture. The cooled tortillas are counted, stacked, bagged, sealed, and packed into cases. Corn tortillas and taco shells follow a different path. Corn masa is prepared from treated corn flour or cooked corn dough. Water is mixed into the masa until it forms a soft, cohesive dough. The masa is sheeted between rollers into a thin band. A rotary cutter stamps round tortillas from the moving sheet. The cut rounds travel through a baking oven. Heat sets the masa structure and reduces moisture. For soft corn tortillas, the pieces are cooled, stacked, and packed. For crunchy taco shells, the baked rounds continue to a frying or forming stage. In the shell fryer, each tortilla is folded around a shaped mold or held between curved guides. Hot oil surrounds it as the tortilla becomes crisp. The curved shape locks in place as moisture leaves. The shell exits golden, rigid, and open, with enough strength to hold filling while remaining brittle. The fried shells drain on conveyors. Excess oil falls away through open belts. The shells cool, then move through inspection. Broken pieces, cracked shells, and distorted shapes are removed. Accepted shells are nested, counted, wrapped or boxed, and packed into shipping cases. Tortilla chips use a related corn process. Masa is sheeted, cut into triangles, baked or toasted, then fried. The chips emerge crisp and golden. They drain, cool, and may be salted before packing. For seasoned chips, a tumbler coats the hot pieces with dry seasoning as they roll through a rotating drum. Sauces are produced in stainless steel blend tanks. Water, tomato paste, vinegar, peppers, spices, salt, sugar, starches, and flavor ingredients are dosed into the vessel. The agitator keeps the liquid moving as powders hydrate and pastes disperse. Heat may be applied to activate starches and develop the correct thickness. A mild sauce must flow smoothly. A thicker sauce must cling to tortillas or fillings without running too quickly. The sauce is mixed until it reaches a uniform color and texture. The finished sauce passes through screens or filters that remove oversized spice particles or undispersed material. It then moves to a filler. Sauce can be packed into small portion packets, larger pouches, or containers. Packet film unwinds from rolls, forms pockets, receives a measured sauce dose, then heat seals around the liquid. The sealed packets are cooled, inspected for leaks, counted, and packed into cases. Larger pouches are filled through nozzles, sealed, coated, and boxed. Cheese sauce begins as a dairy-based liquid system. Cheese ingredients, milk components, water, emulsifying salts, fat, and seasonings are blended in a heated vessel. As heat rises, the cheese melts and disperses into the liquid phase. Emulsifying ingredients keep fat and water from separating. The sauce becomes glossy, smooth, and thick. Agitation prevents scorching and keeps the mixture uniform. Once the texture reaches the target flow, the sauce is pumped through heated lines into pouches or containers. It is sealed hot, cooled, and packed for later reheating and dispensing. Shredded cheese follows a different factory route. Blocks of cheese are chilled until firm enough for clean cutting. The blocks pass through shredding blades that cut them into narrow strands. The shreds may be lightly coated with an anti-caking ingredient so they remain separate. The shredded cheese drops into weigh hoppers. The correct amount enters bags. The bags are flushed, sealed, coated, inspected, and cased. The final product remains loose and ready for portioning. Beans are prepared from cooked pinto beans or a bean base. The beans are hydrated and cooked until soft. They are mashed or milled into a thick paste. Seasoning, water, and fat may be blended in to create a smooth, spreadable texture. The refried style filling is packed hot into pouches or containers and sealed. Rice components are made by cooking rice with water, seasoning, and color ingredients. The grains absorb liquid and soften, while mixing systems prevent clumping. After cooking, the rice is cooled or packed hot depending on the format. It must remain separate enough to portion cleanly without turning into paste. At the restaurant production line, these prepared components are reheated, held, and assembled into finished menu items. Seasoned beef pouches are heated until the filling becomes fluid and ready to dispense. The beef is loaded into holding pans or dispensing equipment. The sauce-coated crumbles remain moist and portionable. Tortillas are warmed on heated surfaces or in steam heating equipment. The heat softens the flour tortilla and makes it flexible for folding. A cold tortilla would crack or resist wrapping. A properly warmed tortilla bends around fillings without tearing. Crunchy taco shells are held dry and protected from moisture. Their texture depends on low moisture. If exposed to steam or wet fillings too long before serving, the shell begins to soften. The assembly flow keeps crisp shells separate until filling. For a basic taco, a shell moves into the assembly position. Seasoned beef is portioned into the center channel. Shredded lettuce adds a light, crisp layer. Cheese is added on top. The filled shell is placed into a wrapper or sleeve that supports its shape.